Hi, this is Codeweaver, and welcome to Codeweaver Writes Code. So, this is the second episode that I have attempted to do involving live coding. I have only been doing streaming for a little while, and I have only been doing live coding just once before, and I found it a lot of fun. I thought I might do a little bit more of it. I am mostly doing this for my own amusement. I hope it might be educational for other people, but yeah, I write code for a living, and I tend to use a lot of C# in my work. But I started out doing a lot of my programming in C++, and more recently I started exploring Haskell because I found I wanted a new challenge and a new way of thinking. And of course, it's a very old way of thinking because functional languages have been around forever, but Haskell for me satisfies the same sort of desire to get sort of performant code that I got out of writing in C++, but does it in a different style. So there you go. And lots of other great languages out there. I quite like C# as a practical language, and it's got a few features I wish C++ had. But I just do too much of it. So this is why I've chosen to do C++ and Haskell, at least for now, on this little project. And this project has involved not this code here. I'm going to switch over very quickly to, oh, hang on, I don't have that on screen. Well, that's good. That means I don't show you the thing that I didn't want to show you. If you've been following the previous stream, of course, you know what all this is about. So hang on a second. I'm going to go to this. So here we go. We have, ignoring the bottom half of this, because I was exploring variations that I want to eventually get to, I decided to pick generating Pythagorean triples because it is a relatively simple to understand problem. So actually implementing a working solution in any language shouldn't be too much trouble for someone who has familiarity with whatever their personal favorite language is. Feel free to try it yourself. The idea is to generate a list of triangles listed as a tuple or a structure of three elements, or if you like, a list of three elements, whatever suits your fancy. It doesn't really matter to me. Sides A, B, and C of a triangle. It's a right angle triangle, with A and B being the shorter sides with a right angle between them, and C being the hypotenuse. Finding those values where A, B, and C are integers. More importantly, or in addition to that, the list that is produced is ordered by C, B, and then A, so that it's listed by length of the hypotenuse. And we want to find the first ones. I guess it kind of isn't really isn't really specified here, and that is list contains the lowest possible values of the triangles, so ordered. So basically speaking, it does say give the output as an iterable container of three tuples of lengths of sides, but we specifically want the list to have the lowest possible values. So you could have one with really, really big A, B, and C, but I don't want that listed unless it happens to be within the first n that are in the list. So by this ordering. So that's what I've been working on. And there's no common factor between A, B, and C. That is that none of these triangles is a multiple of a smaller triangle. And that would happen if there were a common factor between them. So that's the problem space. It's actually not a very complicated problem. And in fact, I'm not even going after necessarily getting the fastest algorithm out of this. The purpose of this stream is, as I said in the last stream, to explore solving this in two separate languages with roughly the same algorithm, but finding the different ways that those algorithms are expressed in the two languages in sort of canonical ways. Now, to start this off, in the C++ side, we've already got this written. We did this in the last stream. We've got a structure to contain it. I decided to do this rather than a tuple at the last minute because I found that that listing out the names individually was better than having a tuple with possibly unnamed fields for each of the positions. This serves just as well for the purpose. There's no harm in doing it this way rather than a tuple for any of the things that I want to do. And we wrote some code for doing tests on right angles, for being able to output the triangle, for being able to compute the GCD of 3 different values in order to find out if they do have common factors as part of filtering. And the primary operation of this is this. It is PyList, which stands for Pythagorean list. And this is done by nested loops. And it does exactly what it says in the tin. It spins through 3 separate loops, nested one inside the other, with limits on the values. The hypotenuse goes from 1 to n. Within that, we have an ordering where b goes from 1 up to, but not including c, and a going up to, but including b. And by doing it in this way, we simply search all possible tuples of 3 values, triples of values, of integers that could possibly form a valid triangle. And if it satisfies being a right angle triangle and having a common factor, we push it into the list. And I realized before anybody points this out, yes, I understand you don't actually have to do this inner loop. There is a way to only do this with 2 loops that's faster, but that wasn't really the point. And I will make a faster version of this eventually. But this is really, really easy to understand. Just generate all possible values of a, b, and c that make any kind of sense, because c is the longest side and a and b have to be smaller than that. And specifically because I want the triangles to be listed where A is always the shortest side, C is always the longest side, and B is in the middle. We have A limited to being less than B, and so on, all the way up the chain in this for loop. Very straightforward implementation. Does what it says in the tin. Runs pretty good on a modern machine to generate values where the hypotenuse is, say, less than 1,000 or less than 10,000 if you're willing to wait a while. That's it. Very straightforward and simple. What I then did was, there's some support stuff down here for verifying that we got the right result. This whole thing I wrote on the stream is to analyze the list and the triangles to make sure that all of the conditions that I set out are satisfied. This wasn't necessary to solve the problem. This was sort of my way of proving to myself that I didn't make a mistake in the generation. This is sort of a checker after the fact. And this is something to just dump out the resulting list in a slightly pretty fashion, even if it's a super long list, and then it sort of truncates it. It outputs the start and the finish of the list. Had some unit test stuff and a couple of tests involving the primary tests involving validating that it works by using the analyzed tries, and then also doing timed tests because I wanted to test on a large scale the differences between the C++ and Haskell implementations on my machine. And I'll go into that later. This is, again, not about ultimate performance, but more about expression in the language. But I still wanted to find out, as we used more features or capabilities or styles for the specific languages, how that affects the actual performance. And so I did want to do at least some preliminary timing tests, and I don't use a complicated profiler. I just use a start time and an end time wrapped around the actual evaluation of the thing, gotten from a system clock somewhere, and then calculate the time that's elapsed. Not a really, really accurate way of measuring time for reasons I won't go into, but it's good enough for loose approximations of getting an idea where things are going. So this entire program ultimately boils down to the generation of values that comes from this. On the Haskell side, I have exactly the same code, and there's that same function, and this is done in a very non-Haskell-y way. It doesn't get quite as far as using sort of Haskell's imperative style sequential operations that are done in what's called the IO monad, the place where you are forced to do sequential things in order to do IO and a bunch of other stuff. This is done more in a purely functional form that uses recursion instead of loops. And it's a little harder to see, but here is basically the loop construct here, where we have a function where if we've gotten to the end of the loop, we just return an accumulated result. And if we're not at the end of the loop, we do a bunch of work. Down in this section in order to do work for this loop, and then we call PyList with a new accumulated value and an incremented value of the loop. The reason why we go to all this trouble is because Haskell does not allow mutation of variables. You don't mutate variables. You bind expressions that are to be evaluated to a name so you can refer to it, but you never ever change that binding. At least not in sort of the pure computation part of Haskell. I'm not going to get into when exceptions apply, but the idea is that you just don't change variables. And the problem with loops is that you change variables. So, in fact, you mutate a variable in the loop here, for example, and here, and here. And in fact, you also mutate this container to push a value into the container for later returning to the outside world. So this has to do each of those layers by recursion. So you can see this pattern, the loop pattern, repeat itself 3 times, and this is where the bulk of that work goes. And in this case, this is sort of what we're doing when we're pushing a value into a container. In this case, what we're doing is we're not mutating a container by adding a value. We are building a new list and returning that list to previous layers of the recursion, if you like. And blending the ones that we get back from lower calls with the ones that we're working with now. So what we're actually doing is we're not adding to a list. We're building a list and then adding it to other lists and then throwing away the ones that we added. Now, that sounds wasteful, but Haskell does this very, very efficiently and often doesn't have to do a lot of the throwaways that we think they're doing. There's a lot of list-related chicanery going on under the hood. Because lists are a very, very fundamental data type in Haskell. A little bit like, say, Lisp in that regard, but of course Haskell has been designed to also be fairly high performance and actually compiled out to native code. So, when last we ran this, by the way, is very non-Haskell-y code. You wouldn't really write it this way. This is terrible. But I wanted to write it in a C++ style and then massage it, which is what I'm about to do. So, but I will actually make sure that I demonstrate that these things run. So this actually generates values such that we produce all of the tuples up to and including where the hypotenuse is 1,000, if 1,000 is even a legal value. And we do that on this side as well as the Haskell side. And of course, this contains a lot of the same functions, in fact, almost all of the same functions that we had on the C++ side, including the ability to dump the list in a pretty fashion. And so let us hit the run operation on the C++ side, and with some luck, you will not be able to see that because, oh, there it is. Yeah, it totally showed up. Huzzah. So here we go. We have elapsed time is 0.16 seconds, and you can see that the list of tries is a bit too long to just dump out on screen. So I dump out the first 3, and then an ellipsis, and the last 3. And of course, I could show all the intermediate ones that are in that list, but that would be probably a longish list. But in order to verify, you can take any 3 of those numbers and show this is a right angle triangle. 696 squared plus 697 squared is equal to 985 squared, for example. And these are all ordered by the C value, which is the last one in the list here. All right. Now, that having been said, let's quickly go and do the same thing for the Haskell side. And so to do that, this requires me to go into Tools, spark up a PowerShell, and I should have already had this open, but I haven't, so we're just going to have to deal. Don't know if that's going to show up. It is. OBS occasionally has trouble recognizing the windows that I'm using. It's all right. So there we go. There is the project, and in this case, we just go stack run, and that is going to do exactly the same thing on the Haskell side that it did on the C++ side. And as you can see, it produces the exact same list. And you should be able to see in the screen that this is the case. It took a little bit longer. It took something like 8 times longer. And you could very much argue that's because we're doing a whole bunch of lists. Lists are not necessarily a compact representation. We're doing a lot of, we're not in the Pythagorean case, in the C++ case, the only thing that we're doing is generating one output list, or one output vector, as it were, which is basically an array format of structures. Very, very compact in memory, very efficient, and we're only ever adding to it. And although it does have to reallocate when the array is insufficient, or when the vector is insufficient size, it's still a very, very efficient way to do this, and not the most efficient we could make it, in fact. But Haskell is apparently even slower, and arguably the reason for this is we're doing everything with explicit lists, and because we have done all of our own manual recursion, it is really hard for the compiler to work out how to do any optimizations on not generating a lot of intermediate lists and throwing stuff away. So, yeah, not super fast, but we are going to fix that. At least we're going to do it in a more Haskell-y fashion and see if that improves things. Let's go and try that out. And so I'm going to temporarily close that window. I hope that goes away. Yes, I'm going to leave the other one open, I think. Hopefully it doesn't get in the way of the coding. That is kind of an awkward spot, though. So what I'm going to do is I am going to tell OBS not to display that for the moment. There we go. And we're going to go back into the code and figure out how we want to do this. Now, there's a lot of sort of maybe not the best Haskell-y stuff going on in other sections of this code as well that I might be able to improve, but honestly, the only one that really matters for our purposes is this guy, PyList by nested loops. This is just terrible. So we're going to change this. We are going to change this, and we're going to call it something new. It's still by nested loops. Let me see. How do we want to do this? The first version of this that I want to alter this to is right now what we're doing is we're building up all these tail lists. Building up all of these lists in the innermost part of this loop, and then as it comes, as we build it up, we are concatenating the list that we just generated up here. The list that we just generated becomes is concatenated with the one that we already had, and so each layer generates lists that are composed of sub-lists that are all concatenated together. And eventually all those get fused together, and at the tail end we reverse everything because it tends to build these things backwards. Or it does build these things exactly backwards, and so we need to reverse it in order to get the same list that we get on the C side, and to get it in the order according to the specification that we wanted. So I am going to take all of this, or at least I'm going to take the start of this. Maybe I'll just rewrite it. I'm going to comment this out. This is how you do a Haskell comment in block form. And I unfortunately don't have a Haskell-aware editor. They do exist. There's quite a few of them, actually. But I decided to do this in Visual Studio, and I haven't found a plugin that does it yet. Even if it just gives me syntax highlighting as well as code commenting features and the like, I haven't found it yet. I may find it eventually. I could have used another editor. I wanted to do this all in one editor, so I will be doing a lot of manual editing. But that's okay. I can live with that. I can type reasonably fast, and I'll just cope. And so will you have to. So, haha. So, I am going to rewrite this, but it's going to have, I'm going to call it, actually, if I call it a new name, I don't have to uncomment it. But I will anyway, just to make sure that I don't accidentally call it for some reason. So what we're going to say is that we are being given n, the maximum size of hypotenuse that we're after. So what can we do here? Well, we could rewrite this. So instead of generating the lists generating the list backwards and having to reverse it, that we generate the individual lists. Like we're starting our count from 0 and going up to 1, but then we're pushing it into a list backwards. We could start it from 1 and go down to 0 and try not to end up with this reverse at the end, but that's probably not the thing that's killing us. The first thing that I'm going to do is try to do this in a fashion where the list generates itself lazily in a forward direction. How am I going to do that? I am going to I'm going to say something like All right. So what I'm going to do is I'm going to, instead of providing an accumulator, because that's what this parameter was, it was the accumulator that I fed through all of the loops, and then basically that accumulator ended up coming back out after it had built upon it all of the individual pieces that I wanted to accumulate. Instead, let's try doing this in reverse. Yes, I know, there are lots of higher order functions I could do this with, and I'm going to get to that eventually, but this is an exploration here. So we are not going to pass in an accumulator. We are going to say PyList1, PyList of, we're going to have 1. We don't have to pass in n because we know that that's the maximum. That is, in scoping terms, this n is available all the way through the interior code because everything is scoped that way. So I don't have to pass in n inward. So we're going to go where PyList_C. The pattern match for PyList_C0 is going to be the empty list. And this is going to be at the tail end of our list. We're going to try to build this in the correct direction. This is not quite what I want to do. I'm not going to count backwards. Am I going to count backwards? No. I don't want to keep doing n-1 calculations. What do I want to do here? Actually, I'm going to keep this somewhat simple and do the if clause as I did before. If this is going to be, I guess it's going to be C. If C is equal to n, because this is the same logic I used up here, right? Or C is greater than n. C is greater than n. Then the result of, so whenever we do a binding, what we're looking to is to bind this name or this function with this identifier with a parameter function. We want to bind this to a result. So we're not in the if-then statements saying what to do. We're saying what the value is. And so this is literally the value of this is going to be the value of this entire if clause when we get done. All right, so this is going to be the empty list. If we get all the way to the top, then we have nothing left. All right. Otherwise, the result is actually going to be we need to get all of PyList B, that's the inner loops, values, and we're going to start then we're going to start at 1, and we know that we're going to go up to only C, but we have C in scope, so that's fine. So this is actually going to look at least a little bit like this, except we're not passing an accumulator in. In fact, instead of passing in an accumulator and building it backwards, we're going to generate the list forwards. So this is going to be, this is still not super Haskell-y, don't get me wrong, I understand that. So we're going to start at 1. And that is the end of the else. So I think So that's where pilot C is equal to that. But we need to be able to have C, the limit C available inside of pilot B. I don't want to pass it into each call, so the function pilot B has to be buried inside pilot C if I want to reuse it. So there's a couple of things I could do. If I put pilot B out here as a definition, I want to be able to refer to this this current value that's in operation during the pilot C loop. And actually, hang on, this is not quite done. Because what we need to do is we need to say we want to get pilot B plus appended to pilot C operating on n-1. The problem is I want pilot B not to go up to n-1 but to c-1, so I have to have access to C. So I could do pilot B1C and then have this take 2 parameters. It's a possible thing. I could do it that way. The other way to do this, so that would have to be basically B and I need a new variable name. I'm going up to C, but I actually need it to be its own n. And actually, I'll call this NB, the limit for B, or the end B, NB. I'll call this NB. I don't have a corresponding parameter for pi C because I can just directly refer to n. I don't really like this asymmetry, but it does mean that my code isn't going to have this nested inside of the definition for this. So why don't I do it this way? This is fine. So if B is less than, if B is greater than or equal to NB, then the result of this, hang on, is going to be, again, the empty list at this level. And then pi list, else pi list B, the result is pi list A, and then 1, and our limit is going to be B, and then we're going to tack that onto the recursive call to pi list B, which is it's pi list B of B-1. And this is actually not n-1, sorry, this is C-1. So that's B-1. And the next thing that we can do, pi list A, and A equals if A is greater than or is greater than end B, and so yeah, C has to be bigger than A and B, and but A and B are allowed to be equal. It never is in a practical solution, but it's the way I wrote the spec. Then so it's just doing the same sort of loop. It's end A. Then that else, and this is where we do this bit of code here. This is, we want to build a try. And this is going to have to be an aware clause. So there's going to be aware, because you can't just do else and then do a binding like that. It has to be else and a value. But a value can have aware clause with additional bindings. So this is going to be the result of this list is going to be a single value try. We have to figure out, okay, this is going to be a problem, because if we filter this at this level, we might have a try, we might or might not have a try. So we need to know how do we want to say? We need to say whether or not. So this is going to be called possible try, because we may throw this out. We basically need something like this logic here, because we might want to do one of two things. We're either going to return the empty list, or we're going to return a... We're either going to return one of two things. We either have to return just... Here are our two possible things that we have to return. We're either returning pi list A and... pi list... hang on. Gotta make sure this is all consistent. I need the end condition here. Pi list A minus 1. And A. So we're going to increase A. It's not A minus 1, it's A plus 1. I'm confused as to what I've done here. No, I had plus 1s here all the way along. I don't know why I did minus 1s. Boy, can you follow the logic as I am writing this, because I know I can't. So that should fix up any confusion on that issue. So we're increasing this so that eventually we get to the point where C is greater than N and we end the list. So this has to either skip over this try by just going to the next one and producing that result as this one's result, or alternatively, we want an actual try connected to the remaining values, like that. These are the two things that possible things that we need to return. The condition on which we return that is if, and we want to say something like try is valid, and then we want to do this. Try is invalid. We want to do this. Try is valid. Then we want to return that as the value, and that's where the where clause comes in. Right, where we start figuring out how we want to do that. So here's what we're going to do. You can't have, in Haskell, they're ignoring lower level stuff that we're not going to get into. There's not really any such thing as a pointer or a reference. A variable just is a variable. Now, whether or not it's represented by a boxed value or an underlying primitive because the compiler has boiled everything away or whatever, it doesn't matter, and it shouldn't matter to you. But there's no way to say that a value is necessarily null. Like there's no, like in Java, setting something to null. There's no way to just say this doesn't have a value by way of that kind of mechanism. But what we do have is the ability to effectively wrap up a value in a structure which indicates whether or not it's valid or not. And this is like C++'s optional, variant. No, wait a minute. It's optional in C++. Variant is one of its cousins. And in C#, it is... I've forgotten C#, optional type, and it's optional in C# as well. So, and C++ is in the standard template library. It's called std optional. So it's basically something where you can say that a value is valid or not without having to have a null, which is like a pointer or a reference or something. Regardless of the syntax that's actually used to set it to nothing, this is just a structure. So we're going to say that the possible try is, and the type is called maybe, and a maybe has two possible values to it. It's either just a value, any kind of value, or it is alternatively, this is not real syntax, I'm just typing this out to type it out, or it's nothing. And if it's just A, it contains an A, and that's its value, otherwise it's nothing. That's the only purpose it serves. It's used in it's used as one of the, unfortunately, largest number of error return mechanisms. It's a very common way to do something where something is optional but is not a pointer or reference to something. And since there are no pointers or reference in Haskell, this is one of the stronger ways to do it. It also means that the nothing value does not have to be one of the values that the thing you're returning could possibly be. Returning -1 for a string length, for example, might indicate a certain condition, but that -1 is the same type, an integer, as the rest of the values. Problematic error handling. So we're going to say that this is just a try, and I don't think I can get away with this. I might be able to, because this syntax might not be separable from this, so that it thinks that this is just one parameter. I don't have a precedence issue. I'm going to try that. So possible try is just try blah. And so we're going to say, and actually we're going to say, we're going to do this way. We're going to say, we can actually probably do, we don't even have to do this. We don't have to use just try. We're already doing a test for validity. So why not shove this test for validity I'm being ridiculous. I don't need an optional type here at all. I can just say literally this. Except that's got the logic the other way around from what I intended. So what I'm going to do is I'm going to put this here. Why add more if clauses if you don't need to? Now, take a look at how this works here. It's saying, and this where has to be, all right, so let's see how all this binds together. Because a where clause has to follow a set of bindings and guards, a binding and a set of guards, optional guards. So it has to follow this. So that and this are associated. And what that means is that when we go to evaluate this, we ask if A is less than end A, so this clause is taken care of one way or the other. If we fall into this clause, it's going to ask the question if the triangle is right angles. And it doesn't. It's going to find this identifier by looking in any of the available variable bindings, including like ones that are coming in, including anything that's in a where or let clause that is within the appropriate scope. And so it's going to find this try by going to look for it down here. That's where its definition is. And it's going to, it's got this other clause here as common factor, which uses A, B, and C. A is here, but B, it does not have access to. So that's a problem. We do not actually have B and C at this scope. Again, I could design this so that these were nested parts of these, and I possibly should have. In order to not to have to pass them, thread them through. But you know what? Let's just thread them through anyway. So we're going to do this, which means we have to alter. I don't like doing this. This feels kind of icky, but we're going to do that. And then we're going to do B and C here. And so we're going to do B and C here. And we're going to do B and C here. And so now we have access to local versions of B and C. Again, if I'd indented this and put this entire thing as a where clause to this binding, kind of like I did here, then I wouldn't actually have to pass these in explicitly. I'm just going to do it this way because it keeps everything off to the left. That's not the worst thing in the world that I can possibly see. So this, in principle, should work very, very similarly. We didn't have to use the maybe. And its operations, so we'll save that for another time. This is still not very good Haskell, but the one thing I wanted to demonstrate here, and let's make sure this works, is what this does is it keeps producing the tail end of the list, and I'm going to exemplify that by doing this. Pi list a tail is equal to, and I can literally, this is a common piece of common thing here, so we're just going to pull this all the way out. Pi list a tail. We are constantly producing what effectively amounts to new data prepending a tail. This is the tail of this, because it's the b plus first and more of this loop as a big long list, and then I am concatenating it with we're basically prepending it, concatenating it with a shorter list, which is the interior loop. So this is a big long list, but the big long list is at the tail end, right? And so, and even in here, what we have is we're prefixing a single try onto a big long tail, and the tail is basically just this. Now I could have tail this listed up as a tail and this listed up as a tail in its own functions, but then I'd require where clauses there, and I'm only doing it once, so I'm not factoring it out. The point being is this is building it back, building it front to back, and it's doing it in the correct order, so no reverse is necessary. And the question is, why didn't I do this before? Well, I totally could, but when you take a look at this, it makes you ask the question. It makes you ask the question: is this first of all, is this concatenating lists in a way that builds up having to walk big long lists a lot of the time? Because I said in the last stream, one of the problems in doing concatenation is that in order to properly do a concatenation, even lazily, eventually you have to walk the list, do work to walk the list, in order to tack on the tail end of the list, tack on something to the tail end of a list. And that is still technically true. We do have to do that. And the one thing you don't want to do is if you repeatedly add, for example, one element to the end of the list, then you are walking all of those intermediate lists all of the time. This shouldn't suffer from that, because when it goes to peel away, for example, this element here, when it goes to eventually peel away this piece, it's going to be able to peel away this and lazily leave the rest of this tail unresolved by way of its function call. This function call is literally stuffed in as the tail end of this list, with a possible try. Oh, I forgot to add this. With a possible try stuck on the front of it. So it's individually peeling off elements, and it never actually gets to have to evaluate anything in the tail of the the tail end of the unevaluated list until it actually gets there. You do have to be very, very careful, because repeatedly adding single elements into the list will hose you. If you were to do literally, because it basically boils down to generate me a new list and tack an element on the end. We can go into that maybe in a separate separate video where I talk about some of the ins and outs of Haskell. I'm not really interested in doing that right here. Because this is lazy, though, effectively, we can argue that for the innermost list, which is the simplest version, if the result that I feed back is a single element followed by a tail that's evaluated by a function, we can always peel off the beginning element without having to evaluate the rest of the tail. And when we go up a layer from that and start appending each of these lists at the tail end of this, it's not even going to evaluate, it shouldn't have to evaluate any of these elements until it's walked through each of this shorter list, and as it does so, lazily defers having to evaluate this for each of the values of this that it pushes out, that it publishes. It's going to peel off peel off each of these elements one by one, and eventually, when it gets to the end of this, having done work to defer this one step further, will basically start peeling this off afterwards. So hopefully this is not going to get us into a position where it underperforms because it's turned an append to list O squared operation. It should still be linear. And it does so in the forward direction. It's no more linear than this, but hopefully this should work. I have explained that very poorly because it's very hard to discuss that when it's buried in 3 loops here instead of just talking about a single append in a much simpler loop. So I'm going to stop babbling about that, and I'm just going to build this and see what happens. And I've got an else somewhere on line 83 that it does not like, because I forgot a then. It's fine. And I can't compile it because I commented out the function in which it is being called. It's being called in so many places that I'm actually not going to try to comment that out. This is by nested loops 2. So what I'm going to do is in the timing. So I'm going to do the correctness first. So we're going to do another pair of these. Don't even know why I call it big test 0. Okay, because that's not very indicative of what I intended to do. But this is where the big tests occur. All right, so let's go into let's see, timed tests, primary tests. We're going to do. So we are going to do a little bit of renaming here. We're going to call this PyTest by nested loops correctness. We're going to do a rename of all of those. Right. So what we're going to do is we're going to do temporarily, we're going to factor this out because we don't want to worry about that one. And we're only going to do a big version of this, and we're going to have both of them listed here. So we're going to do by nested loops 2 correctness, and we're going to do by nested loops 2 training. Timing, I mean. Then we can go up into here and we're gonna have to clone these, but that's all right. Now I could abstract the copies of this code in order to just pass in the function call to do the timing. But I don't think I'm going to for the moment. I may do that as a, all right, so that's by nested loops 2, by nested loops 2. The rest of this code is the same, which is why this is a perfect candidate in principle for just being abstracted away. But the problem is I would need to be able to change these labels as well, and I don't want to come up with a complicated way of sorting that out. Actually, what I want to do is also do this. Put I want to do that up here because I want them to be individually identifiable more easily. So the problem is I could pass this guy in to a function which does all this work for me, but then I'd have to find a way to print out that string as a result, and I can't really print out the name of a function from the function alone. And so it's not complicated enough for me to worry about it. I'll just clone the code as long as I've relabeled everything appropriately. So let's see what happens when I do that. That is not what I wanted to change to it to. I'm just leaving. Is right angle try. So this is at 81. What did I leave that was maybe related in here? Because I had a just in here, I was trying to turn that into a maybe value. But I decided against doing that because I didn't need to have the maybe value in there. We do not have enough arguments because I kept, right, that's in PyList tail requires, so that's end A, B, C. In order to call PyList A, it's 1, 1B, and C have to get passed in. I don't like threading those values in, but all right. PyList A is applied to too few arguments. Why is that? PyList A 1, end A is B. See, I could actually I could actually use end A as if it were B, but I don't. No, I can't, because can I? I could actually. I'm not going to. I'm going to have the limit that I want A to go to and the individual parameters listed separately. I know it's silly, but it helps keep the concept of what this value is separate. I could clean this up. It's not going to matter much to the performance. And in the end, in about half an hour, all of this is going to be gone because we're going to do this in a much less silly way. I mostly wanted to do this to show that you can generate a list from front to back as long as you are defining the list as you're generating it, such that the tail is always a sort of a deferred operation. This will happen quite a bit if we ever have to build lists manually like this again. We'll look for ways to exploit this kind of thing. Let's start from the top. We want to pass in to PyList 1, a PyList B 1, the limit that we're going to go to, and a copy of myself. Seems so silly. Yeah, this is silly. It's totally silly. Abandon ship. Not going to do it that way. We're going to do it that way. We're not going to have an NB. We're just going to have a C. This needs to be an ABC, which means that this is call down here is going to be an ABC. It's PyList B, BC. So we have one fewer parameters to pass in. That has to be A is greater than B. Then we do the empty case. I don't have any of those end A's and end B's anymore. That's all right. I still have to pass in the extra parameter that I don't like, but whatever. Right. 1 BBC, that is incorrect. That's here. I'm no longer passing in B as an end value because B is its end value. So there we go. Let's try this again. Now, amongst things, we're not doing we're doing both time tests, and take a look at this. They come out to be exactly the same value, except I'm going to make sure, so it's nested loops 2. So let's just double check that that's actually getting called. So I just want to be absolutely convinced. PyList by nested loops 2 timing calls by nested loops 2. Correctness calls 2. And then in the actual call down here, that calls 2 for correctness, and for timing. So in fact, and we're going to actually maybe put Sterling, put a break between the two sections. Yeah. One more time into the breach. So. So we can actually see that I'm not sure I trust that time, actually. That seems like a suspiciously small time. And so we're going to go and figure out why that is. Because, so that would be in, so nested loops 2, it calls that, it does the analyze tries. Where's by timing? Because of the way I'm doing timing in Haskell, it's entirely possible that it somehow manages to optimize my attempt to time it completely out of the loop, which would be frustrating as all get out. So I got to be very, very careful about that. This may be something where I go off and hunt. But you can clearly see it's not taking an outrageously long amount of time because I'm doing all of those appends to the end. The appends to the end are not accumulating from the beginning of a list each time. It's always the list that I'm defining with an append. All of the other appends are in the tail. The big problem comes when you keep trying to append by starting at the beginning of the last list you appended to, which is not the case here. So really elapsed time 1.5 e minus 6. I'm having a really hard time believing that. That is kind of nonsensical. Okay. So here's what we're going to do. Just to try to debug this, to see if the timing is even remotely sane, because I just don't believe that number. We are going to go into timed tests, and we're going to comment out this one. Whoops, not with that comment style, that comment style. We're going to run it on its own, for one thing, so that there's no dependency that can possibly come from the other evaluation. That's actually not how completely ridiculous is that? Because is that 1,000 values? Yes, it is 1,000 values. The values that it's outputting are consistent with the C++ version, and when we're in the C++ version, we get elapsed time 0.13022 seconds. It's supposed to be in seconds. If we take this up to 10,000, just for giggles. So I'm just running the C++ version, and which you can't see because unfortunately I turned off that window. Why don't I turn that back on for you? In fact, I didn't even show you the, boy, gotta keep fiddling with, alright, and that one's not actually showing the console in question because it should be that one. So this is taking a while to do the generation, even in release mode, for 10,000 elements on the C++ side. I expect it should do the same thing on the Haskell side. But the thing that weirds me out about that run, I'm not going to try to run both timing at the same time. I'm just going to let that run. It is done in release mode, so hopefully that's going to give me a result back with an actual elapsed time. Eventually. That is up in the millions and millions and millions of tests because it is doing a triple loop on 10,000 elements. That might be a little bit overkill. I'm getting Getting bored. Okay, we're gonna stop this because that's not getting us anywhere super. So, oh, hello. Just when I think. All right, so it generated all the values. The first few are the same, obviously. The last few go all the way up to the 10,000 mark. Hopefully none of them get missed out. So that took 125 seconds. Why don't we try it on the Haskell side as well? Because of Haskell's laziness, it's entirely possible it's doing something extremely clever about reusing a previous computation somehow. But here we go. Compiling, linking. Except here's the problem with that: the slower version of that, which I have. No, I don't have the slower version invoked, do I? I actually commented it out. I was going to say that's going to take 8 times longer, but that's not true because I'm not doing that one. I believe I commented that one out, so it's only doing the timing 2 tests, and you can see it's clearly taking extra time. So I'm not entirely sure what that timing number was, but we'll see what happens when this finally spits out an answer. It could still actually take more time than I really want to wait. So I guess I'm going to put that in the background for the moment. But the fact is the production of this actually worked. The production of the lists actually seems to have worked. Although, you know what I should do? In the correctness category, I don't know ahead of time how many elements are supposed to be in there, but what I really should do is have in the correctness code something that says this. Output the size so I can at least see that the size values make some kind of consistent sense between them. So we're going to do that plus show length of, and this is only valid though if it succeeded. So we're going to do that. Right. Now this is starting to get long enough that I actually want to factor out these tests. Because now I have more of this stuff that's getting duplicated. Length tries by nested loops. So I may have to look into doing that. Actually, I'm going to do the same thing here as well. All right, I take that, and we're going to dump that. So we can just actually replace this one. Yeah, okay, so that elapsed time number is clearly not correct. And that's going to be a problem going forward because I have no way to measure the evaluation of that if it's not going to behave itself. So why did that fail? Why is this failing? Can I debug that while I'm sitting here? Possibly not. It certainly didn't take 6.4 e minus 6 seconds. Interesting. So my time it function in fact does not work. reliably in Haskell, which is not surprising. Getting it to forcing it to evaluate the value at the right time. Like it'll always evaluate a lazily evaluated expression when the value is actually needed. Now, time it doesn't need to know the actual value in order to compute a time. It just has to force the evaluation. It may have optimized. This, so it is using this version. It may have noted that this evaluation is just being returned here, and that this is somehow not useful. To execute. It still should, though, because it shouldn't be doing weird exclusions of operations during this sequential behavior. I'll have to think about that. If anyone else knows a really good way to do timing in Haskell that's fairly robust, let me know, because this is clearly not quite doing it. And I could just at the system level use like a Linuxy or Windows equivalent version of the time function to evaluate the execution, but I don't want to evaluate startup of the sort of environment, the support environment for the programming language. I just want to evaluate a function call, or in the case of Haskell, just evaluate the evaluation of a specific value. Right. Elapsed time 125. All right. Right. So size is 1593, and actually I should make sure that that makes sense over on this side as well. So I'm going to duplicate that line. Basically, where we are doing these big tests, all right, I haven't relabeled these yet. So this becomes PyList by nested loops. Replace all. So we have that. And we're going to take a copy of this. We're just going to say size is tries by nested loops dot size. We're going to do the same thing here. How did I do it over here? I actually had it say do the size, oh, and then just do the elapsed time. I didn't do a replace there. That's not what I wanted to do. I wanted to do this. Right. Build that, make sure it works. Yeah, I think that's okay. I think that looks like common code. Let us do, sorry, one last build here. Hit the magic run button. Shows up on your screen, that's good. Okay, that's going to tell me if I got the same number of elements, so that even if I got the tail and the tip correct, if I missed out one in the middle, it will identify that. It won't do, obviously I don't have any complicated a way to cross-compare all of the results from this. I could dump them all out to a file and then do a comparison at that level, but I'm pretty confident the code works. So So apparently, Haskell does have a monadic time computation with an IO base already written, one that it uses that might be better than attempting to use mine. Shall we try to figure out if we can make that work? So this is might be able to find this function. So package time it. So we searched that out. But it's not giving me the, I need to find a rating downloads distribution uploaded source repo, homepage, time it, here we go. But that is a package that is not necessarily one of the standard ones. Unfortunate. I was hoping that that function that I wrote would actually do the work. Sometimes tricky to do this sort of thing when everything's lazy and you have to figure out how to evaluate something without the compiler optimizing it away out from under you. So that is 1593. This one is 1593. So the sizes of them are correct. The tip and tail of the list, first few elements, last few elements, are the same in both cases. And I can't do a timing of the Haskell one, but that's not really the point here. I will fix that, and I will actually fix that offline because I don't think I'm going to be able to figure out why that is. So we're going to have to ignore the timing information out of this. Very, very roughly, what I could probably do if I really wanted to push the point, because the amount of time. What if I have a time operation here? Term time is not recognized as the name of a commandlet function, etc., etc. All right. I don't know how to do that in PowerShell, and I'm not going to figure that out either. I could time it by hand just to find out, but I don't much care because I'm not going to actually keep that code. It's not significantly slower. Well, actually, I suppose I could. I wonder if there's... all right. I am kind of curious. Windows 10 PowerShell time command. That is what I'm typing into. This is a measure command that runs a script block or command that internally times the execution and returns the execution time. Okay. That is not giving me an example that's super easy to spot. So let's try this. Measure dash command. Now, unfortunately, this is going to test the entire program, and I'm hoping that because of the length of this operation, the startup and the shutdown of the program are going to be inconsequential in comparison, so we can just get a loose indication. It's going to be Pythagorean triples. No, it's not. I need to find out where the actual executable is, and that's not actually here, is it? And if I just do a stack run, oh, all right, actually stack run might be what I need to do. Okay, so measure command stack run might be enough to do it. except, okay, stack run, and then I need to pipe it to out default. Really should learn how to use PowerShell better. Is that going to actually do its thing? I presume that's going on in the background. I have no idea whatsoever. All right. Not really that interested in doing timing analysis on this. As I said, I guess I'm kind of curious to see how much better that performed. But it's really not going to be a fair comparison anyway. I'm hoping it doesn't feel like it took 8 times as long, but in order to be able to produce that result. But actually, it's also going to time the output to the console. Not that that's a great amount of output. Yeah, not happy that that timing function for me does not work. But in any case, let's go back to the actual Haskell code. So this is all well and good. What this does is it avoids having to build it in reverse order. It avoids having to build it in reverse order, and then reverse it at the tail end. It's lazily tacking the additional work onto the tail end, but it always allows you to extract the first bit of it. We don't keep building up on top of this, having to reprocess this to get to the end, because all of the work is buried in this function. It never gets to all of the additional appends in here until after it gets through all of the appends and all of the work that's in here. So all of these tail ends simply never get touched until it gets through all of this. All it has to do is keep deferring, because this does have to defer this entire list. It'll peel off each of these elements, and the extra work under the hood, which you go and if you implement this operation, you'll find out why this is. Every time you pull off a single element from in here, it has to do a little bit of additional work to defer this by one more element. But it only has to do that that little bit of extra work once for each element in this entire list. So it only really has to do the work of this list, this walk once, in order to finally get to this list. That's the same logic as saying it only has to peel off, do any work. The only work it has to do to defer this is to peel off the single value. Well, in this case, it doesn't have to do any work at all. So I think that is still a linear operation, and it basically defers all the work until the tail end. We could probably do a test of that to demonstrate that is indeed the case, even with append, but probably take us down a diversionary path, and I don't want to do that anyway. What we're going to do... Oh, hey, check that out. Time test complete. Total seconds in order to evaluate that from start to finish was 116 seconds. Think about that for a minute. Check that action out, because that's kind of hilarious. So in the C++ case, I'm much more confident the time function works, because everything's sequential and it's really hard to optimize something way accidentally. I don't know why my time function in Haskell doesn't work, but I'll figure that out eventually. So in Haskell, what I just did was I had to evaluate the entire execution of the program, including console activity and starting up and shutting down the Haskell backend environment, all of it. All of that plus the processing of the function all took only 116 seconds. Yeah, wow. If I run the C++ version again, and I do it without being attached to the debugger, but using my timing function. Actually, I wonder if I can do something equivalent on that side. Let's actually try that. I can actually open up a separate... I said I didn't care, but I am kind of curious. It's not part of what I want to discuss, but I am kind of curious. So opening up a new PowerShell, which... Can you even see that? I don't think you're going to be able to. Let me see. How can I do this that doesn't cause a serious issue? So I'm going to open up a command prompt here instead of a PowerShell, so that has a different window name. I'm going to take a few seconds to say it's going to be 25 height, 80 wide, set the font, show you the window in a minute. Should have probably done that first so that you could see what I was doing. 24, that'll do. I should have done this a long time ago, but here we go. We're going to do 2019 console. That's the PowerShell terminal. I'm going to add a window capture, which is Visual Studio 2019 terminal console terminal. That is going to be connected to that guy. Haha. You like them apples. And dirty bug. Where the heck is it? Copied out to a bin directory that I can't remember how this works. Where, oh where is the executable actually generated for this? CD release. There it is. Pythagorean triples.exe. It's not liking. So that's that. So I can't use the measure commandlet in this case. Okay, we'll just use the internal timer. I'm not using the same timer in both because I don't want to be measuring the startup. I just don't. And measuring the startup and shutdown and the console output of two different languages, that's just silly talk. But because almost all of the work, 100 seconds of the work is in the actual operation of those nested loops, this is not the worst test in the world. I just have to make sure that the amount of work that it does is utterly dwarfs the work done in starting up and shutting down until I fix that timing function. So we're going to let that continue running for a second while I ponder what I'm going to do next. Still waiting out that 2 minutes effectively for it to get through all of that work. $123.912 seconds. Okay. Now, if I were to believe this, and I don't, this suggests that the Haskell version actually ran a little bit faster. That the fact that there's similar times doesn't really surprise me, but the fact that the Haskell version had it faster is just a hair surprising. The only way that could reasonably be true is that it's done a lot of list fusion to get out from under to get out from under, or list fusion, or not generating intermediate lists in order to get out from under like lots and lots of allocations and deallocations, perhaps. And it's managed to it's managed to do a lot of early out evaluations on some of this, where it doesn't evaluate a thing when it doesn't need to evaluate a thing. I can't see where that would be the case for a lot of internal optimization here. But hey, look, there it is in some numbers, that the Haskell version of this actually managed to generate the results faster from beginning to end. The amount of startup and shutdown for the C++ side of things, I don't think would be terribly huge. I could be wrong. Okay. Until I get two timing functions that I think are roughly comparable for the thing you're evaluating, I would not trust these numbers, except in the very grossest sense. But that total seconds does, at least on both sides, does feel like that is the amount of time that has actually elapsed. I believe the C++ timer. I believe the Windows execution timer rather than the Haskell timer that I wrote. Yeah. There we are. All right, so let's move on, because we're belaboring a point. That was just satisfying my curiosity. I'm going to get rid of that window now because I don't think that's particularly important. And I'm not entirely sure why I have two versions. Because it has taken console terminal and tried to reinterpret what window it's attached to. So there we go. So that was an OBS quirk. So, all right. Let's get back to the actual action here, right? Regardless of whether or not that ran faster or slower, or at least somewhere approximatingly the same, and it did feel like it was about the same amount of time. I could have timed both with a stopwatch, I suppose. What we've effectively done here is this forward evaluating list does two things. First of all, it evaluates it front to back. It evaluates it from the start of the list to the end of the list. And as it produces lists values at the start, it's doing a minimal amount of work in order to defer the tail, the work on the tail end of the list, so that it doesn't actually do anything with the tail until it's done with the beginning piece of it. Now, we do have three layers of this. We have basically a list that is formed by repeatedly evaluating, for example, at this outer level, repeatedly evaluating this function for C. So this one is going to produce a bunch of individual lists before it ever comes back to do this. But that means that everything that it does here is going to get consumed before it evaluates anything that happens in this. And the lengthy bit of it is still all in the tail. We never come back and actually ask this to be to have some tail appended to it after it's been consumed, or in fact anything other than this one. So we just never build up a bunch of thunks that are all trying to reprocess the same lengthening lists over and over and over again, which is what happens when we try to do a repeated append at the beginning of an incrementally built list. This is not incrementally built. That's the thing. This is lazily built so that this incremental piece is evaluated before we even look inside this function. This is append later function. It's not done all at once. And in fact, that illustrates another point. If you were to write something like this in C++, by the time that we exited this function, the entire list would have been built. The entire list would have been produced. As it is, when we call this function and return the result of this, the only thing we have is a deferred call. That, in turn, when we evaluate the deferred call, at most, when we ask for a single element, we'll extract a single element, and everything else is a deferred call. Everything is lazy. And the only time it becomes not lazy is arguably, well, I mean, it becomes forced in evaluation when we need the value. It also, it may become not lazy if the compiler decides internally some wizardry that makes it important for it to be so. Look up in the language spec. Don't really care. That's actually pretty astonishing. It worked that fast though. This is terrible, Haskell. Let's fix this. Don't like this at all. And I'm rambling. So this is great, I suppose, in the sense that it shows how you can do explicit looping, but you would simply never realistically do even this. Like probably what you would do, well, one of the things that you could do is simply say, well, what we're doing is we're effectively generating we're generating a list of 3 values and then figuring out and then building a triangle about it and then filtering it after the fact, right? That's all we're really doing. We're saying for each value of C, we want to produce a bunch of values of B, and for each of those pair of values, we want to produce a bunch of values for A, and then we want to basically have for each of those values C, B, and A produce a trie and then do something filtery with it, which we do in the interior here with this test. This is a sort of an outside-in function where we're basically doing the outer loop and inner loop and inner loop, and then finally we get to the point where we're actually doing a generation of a value. But the generation is deeply nested inside this thing. Instead, why don't we try doing this inside out? Why don't we try a situation where we do something like, because this only ever adds to the list the values that are actually valid, which is fantastic, that's fine. But what we could do is do it something like this. We're going to instead generate, what's the best way to do this? We're going to generate a list. We're going to generate. What are we going to do here? I wanted to try to take a step before I got to list comprehensions, but I could be doing many, many versions of this, and it will take literally forever. I know why the time it did not work. Damn. Because now I want to fix it. Okay, well, I'll get to that in a minute. I say. All right. Suddenly popped into my head. So part of the problem here is we're trying to add to the list at the tail end. What we could do instead is a quick refactoring of this might look something like I'm gonna do this. I'm gonna do several stages of refactoring before I finally recompile this. But it's gonna be something like this. Instead of doing this, we're not going to do this filtering at this level. What we're going to say is else. We're not going to put stuff in a trie. Let's actually, because I'm going to go somewhere with this. I'm going to say A, B, and C get appended to this, and this goes into PyList. Let me see. This is this goes into PyList. It's not PyList. This is actually going to be tuple list. Tail. Just rename this. This is actually going to be we're going to call this undefined because we're not going to be calling this directly. I'm going to replace that in a minute. We're going to take out the trie. We're going to take out the filtering. All we are doing is producing all of the individual triples, A, B, and C, just as a sort of a prefix step to this. And so this is by nested loops 3. So that I know that that's unique. Okay, so and in fact, because we don't have this duplicated, we can just dump that in there and shorten this up. So this is literally just producing this list of tuples, and it's producing it lazily just like before. But this isn't, first of all, it's not in the try form that we're after. It's in a list of tuples, because I'm gonna illustrate why that might be interesting to do in a minute. Actually, we don't need to do it as tuples. Why don't we say, let's actually just call it try? And the reason why is because introducing tuples into this is not really going to help the issue. I totally do tuples and then re-extract them from the tuples later, but let's just do this. That's fine. Now this is going to produce all such triangles, all of them, without question. So what we really want is to say filtered tries is equal to, and we're going to use the filter function. The filter function is itself written in Haskell. You can go and, in fact, you can go and write it yourself. Using the standard ones does have the advantage that the compiler has a whole boatload of code rewrite rules that abstractly at the program level can do all sorts of clever list fusion and various kinds of list elimination. And you can go look that up, and I may talk about it at some point, but all I'm saying is try to use the built-in ones because you get the advantage of a lot of compiler behavior. If you're down to doing explicit recursion yourself, you either have a really exotic situation or you haven't thought through how you can do it with built-in functions yet. And if you are writing your own recursive stuff that you're going to use in high-performance code, then start looking into how to do list fusion and the like, or, I mean, any other kind of container-based fusion, I suppose. Because a lot of the really high-performance stuff eventually moves away from lists, but I like lists. They're easy to understand. Compiler's pretty good at using them. So we're going to say we're going to filter these, and this is where we're going to put our logic. So for any given try, we're going to do that. We're going to structurally decompose it, and then we are going to have as the condition all of this. We're going to keep it if it's a right angle and it does not have a common factor. And that is going to be applied to tries. But actually, what we can do here, so let's start with that, okay? So this is part of the where clause. So this is just an inner function that's been built. And so what we're going to say is, so the unfiltered tries, unfiltered tries is equal to, it's going to be the call of this as we had originally. It's this guy. I'm going to tell you why I'm doing it this way, because I'm eventually going to collapse a lot of this to a much simpler bit of code. Sorry, here we go. PyList 1, unfiltered tries. And so this as a value is equal to the evaluation that we wanted, which is PyList 1. Just to bootstrap the loop process. N is defined for everyone, so I don't need to pass that in. But then filtered tries is equal to, actually, you know what? I'm not going to make that a general function. I'm just going to do this. It's just a new variable. Filter tries equals filter, etc., 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 based on unfiltered tries. And then all we have to do is pass filtered tries out. So again, in the where clause, we do additional bindings. We bind a bunch of internal functions to do the loop. We produce all of the tries of every kind, and then we filter them. So does this work? Like, is this any better? Well, let's go take a look. I really do have to refactor this so that I don't keep duplicating this code, but I'm not going to do that this pass, because that's just going to 3 to that, 3 to that, 3 to that, 3 to that, 3 to that. I'm not going to do it now because it's going to chew up stream time, and I already know these get really, really long because I tend to ramble as I think things through on the fly. I think I've got all of that. I am going to miss something, which is why I should do the refactoring. So I'm going to run these two guys back to back, but I'm not going to do it on the 1000 element. I'm going to do a 10,000 element. I'm going to do it on the 1000 element, which means that back in the C++ version, just so that we have a comparison, let's take that back a notch. Let's run that. Hopefully you can see that that's just popped up. I'm going to slide over to the side here. So this basically says how much time that took. Okay, and then I'm going to go into the, no, what am I going to go into? I'm going to go into here, and I have to make sure that I'm outputting both of the last two timing elements. And actually, I could do, so it's bi-nested loops 2 correctness. Okay, so I have to make sure that I am timing and running the same amount of code here. I just want to make sure that the output is actually identical. So I am not going to do the correctness call on that because it's going to take extra time. We're only doing the time tests anyway. And so this is irrelevant. We're only doing the time tests. And in fact, have I done that over on this side? Now I'm not timing. I haven't, I don't think. Oh, I have. All right. I'm not timing from the command line anyway. So I think this gives me loops 2 and 3. So let's find out what happens when I do this. It's given me an execution time, which again doesn't make a whole lot of sense to me. Hang on a second. What did we actually end up outputting here? Oh, it didn't, because variable out in scope try, so it was measuring the compile time, which is not that useful. 108. Yes. 108 says, did I mean variable not, okay, did I mean the constructor try, variable not in scope small try, is right angled try. See, so I need the try itself as well as the decomposed values in order to run this function. Which suggests what I really should do is rewrite has common factor with a triangle function, just to make my life a little easier here. So that's what I'm going to do on both sides. What I'm going to do is I'm going to pop up here, has common factor. So I'm going to add another one here, has in try, and I'm going to, no, I need this guy. Okay, I'm going to reorder this a little bit. We're going to put that up here. We're going to have is right angle, has common factor in try, and we need 2 tries. So sorry, we don't need 2 tries. We just need the 1 try. So we've got that. And we basically call is equal to has common factor. We don't need to reassert this because it'll be asserted up in the has common factor code. Has common factor ABC. That makes our life a little bit easier. I'm going to rewrite this on the C++ side as well. But we're going to do not has common factor in try. try. Shouldn't really be any more slow. There's that. There's that. And now I can just collapse this because why expand it outward? Okay, I'm happier with that. And unfortunately, that measure wrapper is going to measure the compilation time, which is not of any interest. All right. So we have the same result in either case. Okay, same result in either case, but it kind of felt like the second one was quite a bit slower. So what we're going to do is, because we only have the timing thing that takes that works when we have only one thing running, we're going to temporarily take out bi-nested loops to timing. Let's just double check that this is calling the right one. This is calling that one, which generates all of the elements and then does the filtering after the fact. All right. That took a while. That's interesting. That's really interesting. So here's the interesting thing. Not all of the triangles are going to be successful. A lot of them are going to get filtered right away by way of this operation. So we're either going to add something to the list, or we're going to just defer onto the tail of the list, which means that right up front, the instant we evaluate whether or not there's an element here to examine, we're either going to peel off this one as the element that we want, or we're immediately going to go into the tail, which is then going to further on the recursion. Now, Haskell is lazy, so when I go to generate all of the values this way and then filter it after the fact, in principle, it's doing about the same amount of work. In principle, it's kind of doing the same amount of work, because in this one, it actually does explicitly have to have, in this case, it explicitly has to have embedded in it this this append operation, this structural creation here, that is the head of a list and the tail. It has to have that in there in order for it to peel this off. This is going to peel off one of these, test it, and then discard it, and then go on to the rest of this. So the one advantage in doing it explicitly this way is that it never adds this element to the list. It's all lazily evaluated, so we never look at the tail before we examine a head piece. But in this case, there's far more head pieces to look at before we get to the point of having to exclude it and throw it away. So this is an example where, even though Haskell is lazy, the compiler can take a look at, or the code as this is written. This never adds an element to the list in the first place, whereas this one filters it after the fact. Now, I like in Haskell the ability to, for example, generate a collection which is larger than I need. Like an infinite list, or a list with much more elements than I strictly speaking need, and then filter it after the fact, because it means that I can write the generation code often quite a bit more easily. and then I can filter it afterward. Pulling out, oh, hello. I see Dev, I can't even read that because my eyes are going. Dev Cookie Land, hi there, how you doing? I guess you popped in and then popped back out again. I'm sorry I didn't say hi. If you come back in, that's fantastic. I really have to pay attention to the stream more. It's really hard to do when I'm coding, though. I'm finding I have to retrain my brain to occasionally distract myself to look over at the stream. Right. How fun is that? Anyway, but the problem here is that it has to build the list, and the compiler can't see through that and avoid producing this structure. So this is still a situation where even in a fully lazy language, it's worth asking the question, do I bother putting this in the list in the first place? But this does work. I'm fairly certain this, in fact, does take longer than the other one now that I come to think about it. Because it has to generate all, see, it's 1,000 cubed, is it 1,000 cubed? Is that what it's set to? 1,000 cubed elements go in there. Not quite, because because C goes up from 1 to N, but B only goes up from 1 to C, and so on. So it's, I could probably work that out, but I don't want to. Analytically, that's a lot of algebra I don't want to do. But it is still an order n cubed number of values, effectively. And then it filters them out after the fact. Quickly, but it still filters them out. So, in fact, my original was faster. And some hybrid between the two where I'm not constantly passing around these extra parameters would be faster still. Still, this lends itself to a new thought. I'm throwing this one away. I don't think this is useful. It was an interesting experiment because it generated all the triples after before the fact, and then filtered them out with a separate operation. And it couldn't run this. It couldn't push this filter operation through this somehow to filter out this lower level code. The compiler couldn't possibly be that smart. So what we really want is we do want the filter. We do want the filter deep inside there if we can, and if we can't, we use an external filter bit of call like this. So we're going to do this a different way. We're going to instead use a list comprehension, and a list comprehension is going to do something basically, hopefully with the performance of number 2, but with the result of what we just did here. And I'm going to throw this one away entirely. It's you know what? No, I'm not. It's still useful to preserve. I'm just not going to consider that to be particularly fast. But it does lead us on nicely to the next section, which is to use a list comprehension for this. And a list comprehension allows you to build a list while doing filtering, but in a much more compact fashion. And it even has this concept of Cartesian products of nested generations built into it. So we are going to try to do this in a list comprehension and see if we can do better. So, geez. Okay, so it's going to be 4. Amy, so let's go and actually clone this first so that we're ready to go. Right. I think we got everything sorted out there, do we? Except for that one. This one problem doing copy pasta. All right. Copy paste. All right. So. We're good. Let's go and pop ourselves up to. Brain not functioning. Slowing down. Popping ourselves back up to here. List comprehensions. So we're going to get rid of that for the moment. We are going to might be able to do this here. Let's figure out how we're going to do this. So we're going to say we want to have, as the output of the list, the elements of the list are going to look like this. But now we have to, now this is a construction rather than a decomposition. Looks the same because they are the same. It's just depends on where you place them. So, this is given that A comes from, we're going to do C first. C comes from 1 up to and including n. B comes from 1 up including C. And A comes from, actually it has to come up to 1 to C minus 1. And A goes from comes from 1 up to and including B. So that's the first thing that we want to do. And now this should correspond to all of this. Now, I guess the first thing that we're going to do is we're going to do this, and then we're going to do, so actually we're going to actually put these back in. We're going to do this. We're going to put these back in, and we're going to run this as a temporary. This one we really won't keep in its current form because this is just a stepping stone. But there's our unfiltered tries, and then the rest of it is identical. So let's actually run this and make sure that it doesn't explode horribly. And in fact, I realized that I have accidentally left this open. I should have actually shoved it further off to the side. I don't think it's hidden very much. Unfortunately, when I'm typing in the source code window on my physical screen, the other two windows go into the background and I don't see them anymore. But they unfortunately do show up in the OBS stream. So I'm gonna have to figure out how to fight that problem as well as time goes on. But the results of the 1,000 element, the up to hypotenuse 1,000 list is the same in this new case. Did I actually call it? I may not have called it. Let's double check. No, I did not call it. So let's and I have no idea if that's even working. So let's take a quick look down what the heck am I doing street here and check to see whether or not my list comprehension is correct. Oh, yeah, that was a bit dumb. I actually wanted to say filtered tries here, so we're going to do that. We're going to stop this because that's just a disaster waiting to happen. If we can even get it to stop. There we go. And make sure the C++ version of this is put off to the side. And it's gotten horribly confused for some reason. It's not letting me. I do not think this has worked because I am not entirely sure why. So stack GHCI. Let's actually play around with a few list comprehensions to see if I remember how this works. Right. So set prompt. There we go. So we could have, for example, we're just going to do this with a tuple. So if we have, actually, if we have A and then we do a guard, we can, or C and then a guard, and then we can say, or C given that C is derived from 1 to 100. Should we do 1 to 10? I did 1 to 100 anyway, but 1 to 10. All right, so that does what we expect it to do. The tuple B and C is when we have B coming from 1 to C minus 1. And it does not like that. Immediately, it does not like that. Interesting. My laptop on which I'm watching the stream has just faded into the background. How very frustrating. Okay. So we need, I want to know what one, so stack GHCI. Bring it back up, please. Right. So 1 to 10, let's just make sure this is correct. 1 to 10 gives me that. But 1 to 1 gives me that, and 1 to 0 gives me nothing. But that's fine. So why did this fail? Oops, forgot the arrow. So that worked because I allowed B to go all the way up to C. But if I go to 1 to C minus 1, no, that worked because it goes 1, 2, 1, 3, 2, 3, 1, 4, and so on and so forth. So that's fine. And then if I say basically we also have A going from one to B, we have A, B, C. We get, in fact, all of the relevant tuples. Now, it should be produced lazily. I shouldn't have to. I shouldn't be producing a list that's big. That's that big. For example, I could do something like that. Let tup equal. Come on. How do we do this? Do that and have this value actually equal to 100,000 or some really stupidly big number. And that is actually going to force an evaluation? No. So T, what is the type of tup? No, sorry, not bang T, it's colon T, tup. Right, so now this print actually prints out the actual sort of thunk property. And it is in fact a thunk. It's not actually evaluated into any values. And in fact, that would have been billions and billions of elements. So we actually haven't constructed something that's billions of elements big. But I can take 5 elements out of tup. And although there's some memory management issues, it's clearly fighting through. There are the first 4 elements out of that. And then if I say print tup, that's interesting. Why is it? Pythagorean triples is still running in the background. Something is funny whenever I, okay. Something is funny whenever I crash out GHC like that. So let's not take that as gospel. Haskell, Pythagorean triples, there we go, stack, GHCI. Okay, so let me scroll back to where we were. Yeah, so we're gonna have to do something like let top retype this. I'm going to do this for a fairly largish number, a reasonably large number that it couldn't really store in memory. Yeah, I forgot the dash here. So yeah, it came back instantly, right? I don't know what the other thing was. There's a memory management issue somewhere in the back end of the GHCI. So take 5 tup, comes back instantly, and then if we I'm still a little bit surprised that it's listing that out as an unevaluated thunk. I am going to quickly look up because I feel like it. Haskell print thunk. GHCI print. Interactive evaluation of the prompt. IO actions the prompt. The :print command in GHCI prints a value without forcing an evaluation. Value useful for inspecting values that are not normally printable and for experimenting to find out which parts of data structure are evaluated. Yeah, there's :print, :sprint, and :force. Well, :print tup seems to have given me something with effectively what still appears to be it's given me type information, but I would have expected it to actually give me the value. Oh, very curious. This is what happens when you live code. You start looking things up. Well, in principle, I would have expected to see actually a partial evaluation of tup at the beginning of this. It seems to have printed out the type information, but it doesn't appear to have. Let's see. So what can we do here? We can do print a value, show a value without forcing its computation. And that's really what I used to use in order to see partial evaluations. If I had q equals 1 to 10 actually 1 to anything. Let q equal 1 to 10, in fact. I force the evaluation. That is not showing me what I expect :print to actually show me. I expected it to actually show me an evaluated value. It's printing me the type information. That's really weird, because I would have expected, see, that's what I would have expected to get out of like :type, right? If I did :type q, it's not quite. It's not quite. It's saying it's saying that it's an unevaluated value T5. That is really strange. This is not how I expected it to work. And in fact, in working on previous versions of Haskell, that would have provided me information about the about how far or how much of the value was actually evaluated and out of thunks. All right. That is really, really weird to me. And I don't know. I'm running into a bunch of really strange issues. This is the first time I've used GHC via the Stack, which is sort of the package curating system. Stack also allows launching of GHCI in order to be able to do this kind of interactive stuff. This behavior, though, is peculiar to me, because I would have expected Q to be dethunked, and in fact, it should be. The fact that I can let tup be this incredibly huge, from earlier on here, this incredibly huge list, take 5 elements, and I know that the first one came back instantly, and the second one came back instantly, more or less, with the first 5 elements of that list. It should have been at least partially evaluated. That is weird. Force should have actually forced it to a real value. I don't know what this is doing. This is extremely weird to me. Don't know what that means. Not relevant to our discussion. What I need to do is I need to get this all the way down to a really small number, just to see if this runs at all, because the logic of this should be the same as above. This should generate me a list of all of the relevant tries, because instead of using a tuple, I'm using a try structure, and then that I should be able to filter, and then I should just be able to return the filtered tries, and I should be effectively done. So what I'm going to do is clearly got a few tool chain issues to work through, but that's not something I need to worry everyone on the stream about. So that produces 3, 4, 5, the only one that's relevant. If I go up to 100, you can see that, in fact, we got identical results from our 2 passes. So let's go up to 1,000. Hang on, let me just double check here. We're only doing 2 of these, and it's basically 3 and 4, I believe. So let's just double check that that's what we're actually doing. We are doing 3 and 4 being output, so they should basically run to completion in a similar fashion. Yep. Effectively, both of them ran in approximately the same amount of time there. Well, actually, I couldn't tell because I did the first one and then it borked off into the second one, and it should have been using. Maybe it's gotten really, really clever with its optimization, and that second one is in fact reusing values from the first one in some fashion. I can't imagine how that could possibly be true. But this does do some very funky common sub-expression elimination, so maybe it did so. I am not entirely sure, if I am honest. So, but it could be actually as a result of the first one, it did a bunch of memory allocations ahead of time, and then the second one reused the memory. Not entirely sure. That's an interesting one. Not gonna lie, don't know how to interpret that. But what we're gonna do is going to do this. And we're going to run this all on its own. Thousand elements comes back pretty quick, right? But we already knew that. In fact, it's actually coming back a little bit faster than I thought it would. I thought at one point we had this doing. What was our original? It's all right. Did that exactly backwards from what I'd intended. So about a second, right? And yes, I know why this number now looks valid for its output. I know how the time thing is failing. I'll have to go and address that. I need a slightly different function in order to. I'll talk about it later. I will fix that for the next part of this video series that I'm doing. So hang on, we're gonna basically return that to the way it was here. Right, there we go. So this actually works, and I expect though that this is going to be as slow as number 3 was. Because it's going to attempt to do the filtering after the fact. It should be the same amount of speed actually as. So I'm going to actually test this in the simplest way that I can. I'm going to make sure that it runs, and then I'm going to use that measure mechanism to test at least the relative operations of these runs. So. Make sure, where is it back in time here? Somewhere we have this is stack exec. This is some experimental stuff I was doing. So I'm going to have to, because I crashed out the terminal, I've lost that. PowerShell time command. There we go. I'm going to keep that open or memorize this. Measure command. And here we do stack run, which once it's compiled should be fine. Pipe that into out default. So that gives me a total seconds time, which is probably dominated by startup and shutdown stuff. But if we increase the big test size, what we want is stack build. because I don't want to stack clean, stack build. Because I don't want to have to run the entire slow thing twice. I'm going to do the build as a separate step. Okay, I don't know why this is stalled now. Oh, it's always something. All right, pulling up the task manager. Why do I not have my more elaborate task manager in this thing? Fun. All right, we're gonna kill that. Start again. And line, developer PowerShell. Right. Let's make sure that's showing up in stream. Yes, it is. Stack clean. Stack build. Okay. There's my measure stack run. Oh, right. It silently does the thing, and then it spits out all the stuff at the end. That's fine. As irritating as that is, I didn't have to actually reset all that, but there you go. I suspect that this is going to be as slow as the one that does the post filtering, and that's fine because we described why that is. It's like, although Haskell's lazy, it's actually inserting into the list something that it shouldn't, or at least it's inserting. It inserts so few things into the list that filtering it out after the fact is still a problem. The compiler isn't smart enough to like drag the filtering mechanism deep within the the forced loops there. So that's fine. But what we're really going to do is actually this. I'm going to let that run to completion. But what we're actually going to do is this. We need to put that filtering at the place where we're actually building this list if we can. I do like I said, building complex lists and then filtering them down, but if you can avoid putting it in there in the first place, that's great, right? So what we are also going to do, though, is we can actually add, in addition to these where values are derived, where values take on their, the individual values to build take on their values from, I'm actually going to bury this test function, filter test of ABC, and we're going to basically have that as filter test ABC is equal to, and actually that's a problem because all of our filters currently actually take tries, and now we're in a position where that's actually inconvenient. Okay. So we're gonna, let me see if I can do this. I'm gonna say try here. I'm gonna say try comes from just this value. And we're gonna say filter test try. Filter test try is equal to all of that. This is a bit of a weird syntax because we have to do what looks like I think this is allowed. We have to do what looks like a binding inside here that is not deriving from a list. But this is, I think, how this syntax goes, and then this allows us to build the list by by binding all of these values in sequence, binding this one exclusively from values available, and then performing effectively what is a guard test on this. So I'm just going to make sure I can do that. Haskell list comprehension filter. Actually, so this is not the way I do this. I think this is actually supposed to be an expression let try. So that ran in 135 seconds, which is the same slow speed. Actually, that's 135 seconds, which is that the same speed as number 4? Come on, where are we? Or sorry, number 3. Stack build. Still have to fix the code that I just wrote. That needs to go there, and this needs to, oh, that's fine. We are going to temporarily close that window so it's not sort of getting in our way in any case. And I'm going to try to make sure that the code I write is above this bar. So I'm going to, give me a moment. That should be slightly better for making sure that the window that I'm actually interested and focused on is not being, right now, which is the Haskell one, is not currently blocking anything. So measure command, and it's currently running. And I think this one is going to take under 35 seconds as well, which means that prior to me doing this little jiggery pokery here, before I added this in here as a filter test, it was basically behaving like this one, where I generated too many elements and then filtered out too many of them. Where what I actually want is something where it filters it out early, but still does all that looping. So, and on top of that, actually does it in the correct order, because as you saw earlier when I was doing my REPL tests, this kind of code here was generating me tuples that were in the correct order, which means that it matches basically this code here, but it does it in order. So it does it in order like this, in the correct order like this, front to back, without any sort of reversals. But it also has the filtering power of doing the test deep inside here. So this entire function for number 2 is superseded by these loops. Does it share anything with this post filtering? No. This post filtering was a mistake in this case, because the number of things I had to filter was way, way higher than the number of ones that I was actually keeping. So, okay. I mean, that makes perfect sense, and I should have seen that coming, because the compiler couldn't be smart enough to sort of push the filter further and further down on its own, and that's totally fine. Let's make sure that this final one, well, I'm going to wait until this comes back. Hopefully it comes back in a minute. 135 seconds, in fact. Or not. Maybe it's going to come back in 800 and some odd seconds, which is way longer than I'm willing to wait. Yeah. So this one is currently running. Which version did I have this set at? This one is only running number 3, which is the slow one, and number 2, which was the one that was faster. In fact, number 2 was the one that hypothetically actually beat out the C++ version of it. This is going to take way too long, so we're just going to kill that entirely. We are going to try running number 2 again, just to see what performance we should be getting, because that was the good one. Number 2 is the good one, so let's do that. Does appear to be taking a bit of time. There we go. Total time 122 seconds. So that's sort of the benchmark that we want to achieve, because I think, if I'm not mistaken, that's what the roughly what the C++ version was running at for that kind of size of thing. So having done that, we now have a version 4 that actually properly does the filtering at the right layer. So we are going to now we are now going to run the one that we'd actually intended to run. So we're going to do a stack build, let it do its thing. And then we are going to do the measurement and see if that even completes, because wouldn't that be nice? Now let that run for a bit. So hang on a second. Stopwatch 5:19, so we gotta wait 135. So it's actually 2 minutes. That's a long time to wait, I'll grant you, to see if this thing finishes. But what the heck? In for a penny, in for a pound. in any case, this is closer to what I might consider to be a more Haskell-y solution to solving this problem. Where did we actually put that code? That one. PyList by nested loops 4. This is how I might implement the algorithm we actually use. This isn't actually how I would implement it in real life, because I technically don't need that third loop, and we will eventually optimize that away as well. But how awesome is that? Because that code here, is replacing all of each and every one of these, including this one where we did this explicit looping mechanism, which behaves a lot like how C++ did it. Of course, it had to do the reverse at the end, and in fact, by the time this runs, the entire list has in fact been built up and reversed. The act of having to reverse it means that no matter that for all of this code, the entire list effectively has to be investigated. There's nothing lazy about this, specifically because we are getting way down into the weeds on this loop, and at no point can we evaluate even the first element without getting at least as far as this level here. And this is basically done accumulation style, so we have effectively pushed into this explicit constructions of each of the elements onto the null list by the time we get to back to the top here. There's nothing lazy about this operation even without the reverse, because effectively in order to even in order to get the loop out here, in order to get out ACK at all, we have to have fed it all the way in and had it come all the way back out. Whereas with all of these other ones, we've effectively gone and produced a value. Is that actually true? Yes, we've effectively gone and pushed out a value, the head of this list, right away, which we can decompose and pull out without needing to look at either the remainder of this list or in fact the entire tail of this list. We don't need either one of them in order to pull out a single value, so this is far lazier. All right, so 142 seconds to do it that way. How do I feel about the fact that it's actually slower than the explicit looping? That's not fantastic, but I could probably dig down and figure out why that's the case. I'm going to run that again in the background just because I can, but just to see if it's consistent. Keep in mind that it's starting up and shutting down the GHC interpreter, but that is slower by a bit. It's kind of curious. I'm not entirely sure why. I'm really not entirely sure why. That's curious. I would have to think about the code generation in that. Because this should effectively boil down to the one that we actually executed that did appear to be fastest, which was this. In any case, we're in the right ballpark for magnitude of operation. That's just beautiful. All right, so having done this in Haskell, I'm finding that the time is 5:24. I'm thinking I might take a break from this and go on to what I'm going to go on to next, without changing the actual algorithm, without removing that inner third loop to make it super, super fast. What I'm going to do is I'm simply going to take this and I'm going to go back over to the C++ side, and what we have here is effectively actually, there's one more thing I can do. So it's what's interesting to me is there might be a lot of cases where we want to look at all of these filtered triangles, but we want to filter them out early so that we want to have an operation that we can use to filter them out early so that we don't create an element for us to have to later filter in the first place. And that's exactly what we did with basically loop number 4 here, where we have the filter as part of the lazy list construction. This is fantastic, but what this is doing is effectively it's providing this function externally, and maybe that's why this is slightly slower, is that this is not being inlined fully into this filter code. It's being passed in as an external function that it has to call, whereas in this one, the speed may come from the fact that that it's calling global functions that it can link right into as part of the build of all of these loops. So if I were to make a guess, actually now that I come to think of it, that might be the case. This is actually explicitly building up these loops and then explicitly calling the test functions deep inside of here, which it can statically link to, etc., etc. But when we're doing this, in principle, this may be storing an it may not be inlining the call to filter test in order to be able to do in order to be able to do this generation. This may be calling filter test indirectly. Now I wonder if I were to have a I'm going to let that finish once again. What did it tell me? See, that came down to, so what was it here? It was 142, it came down to 138. So we're roughly in the ballpark of the kind of times that we're looking at. I think we're roughly in the ballpark of the C++ version, which, by the way, I'm just going to run again just to... That's not correct because that's not a big enough, it's not the full 1,000 elements. Oh, it is the first 1,000 elements. Ooh, now I'm confused. Have I been running one of these with the wrong number of elements? Oh no, this is 10,000. This is going up to 10,000. Okay. Aye, smart. So debug, we're going to start without debugging. Let's just make sure that shows up in the stream. I apparently have a network error. Why do I have a network error? That's unfortunate. Okay, well, in any case, did I lose the stream? No, the stream appears to be okay. Okay, let's take this and move this off to the side so it's not bugging anybody. We'll be able to see the timed results coming out of that. Okay, so our fastest C++ version and our, or at least our current C++ version and our current best Haskell version they're all about in the same ballpark. I can get down to stricter timing operations eventually. What I really need to do is fix that time it operation, but I'm going to do that in a second, because what I really want to do is I want to find out what happens if I take this and actually have this as not an internal function, and I don't think it's going to matter. I'm just going to quickly do the test like this. See, I would have figured, to be perfectly honest, that the list fusion would have tried to, or the list comprehension would have attempted to not make a call into what should be an inlineable function. But maybe it's only inlineable when it's global. I'll have to check out what the performance characteristics of that are. So I am going to make sure that this is made global, and in fact I'm going to actually just put this all the way up at the top. So I'm going to call this filter test try. We're actually going to call it try filter. We're just going to call it try filter. Really what I should do, if I really want to do this from an optimization point of view, start digging into proper profiling, start digging into looking at how objects are being allocated and deallocated. Haskell is inherently not only a lazy language, but it's a garbage collected language. And you'd think that with all the lists that are going on, you create piles and piles of objects here and there. And that can happen if you're not careful. But it's also the case that where Haskell can find intelligent ways to fuse lists out of existence, it will try, because lists are used everywhere. They're almost ubiquitous. They're almost used as an iteration mechanism, as you can see, especially on collections and the like. And so being able to... Where are we? Oh, that completed with 127 seconds. I'm currently in this one at 138 on this particular implementation. We're about to try one where we are going to do a stack build, this slightly altered version of function 4. Just make sure function 4 is the one that's being called. Yes, it is. Now we're going to measure the output, so we're going to let that run. So I don't prematurely optimize. I'm happy to use loops. There's lots of things like byte strings and vectors and other clever ways of doing high performance processing of batches of stuff that still provide enough built-in functionality so that working with them often looks like you're operating with lists even when you're not, and it just has different strictness profiles and like. It's high performance stuff. I've used that a very little bit, and it's pretty cool, but it doesn't really help sort of teach the language, as it were, and to show you how this all gets stitched together. Other reason this might not be. Try filter has to take a try, but I haven't actually specified what try filter's types are, except that it derives that from is right angle, which then does have to explicitly state what the try is. So in fact, the type of try filter should be completely 100% known. And in fact is geared around a very specific type, which is try, where each of its elements are ints. There's type deduction going on all over the place. I was thinking, is this going to improve if I provide an explicit type annotation? And probably not. It's funny too. So for example, has common factor ABC. There are things we could do to improve the performance here too. We could actually force has common factor to produce unique versions of it for concrete types instead of being fully polymorphic the way it is. But the compiler is so smart about being able to get around a lot of this, to be able to get around a lot of its the way it handles generics in terms of passing around dictionaries. That anyway. Got 135 seconds. Did not make the slightest bit of difference to make it global in this case. And yet, if we go back to number 2, I'm willing to bet that this actually shows a performance benefit. I think it's probably because it's been inlined right into the place where it's producing elements. But that's curious in and of itself, because that implies that it's still fully using lists in order to do its work. So when I look at number 2, I'm still producing individual elements tacked onto lists. It would gobsmack me that that's as fast as, but it's not adding very many. Well, yes, but neither is the other one adding very many elements. Weirdness. I do occasionally get hung up on weird performance issues. So one of the things I was thinking about was with this last one here. You can see that I'm passing into the thing that's doing the generation an actual function that can do the operation. Effectively, I'm passing in. Actually, what I'm doing is I'm passing in a curried. I'm taking a function. I'm applying a parameter to the first element, which effectively produces a Boolean quantity, which is a sort of a zero parameter deferred thunk, which then gets evaluated and then thrown away each time. So that could be why that is slower as well, because that is effectively currying a one parameter function down to a zero parameter function and just deferring that to later, but I'm only ever doing that once on each try. Whereas when I do the explicit loop, I'm generating the same number of elements effectively, but it is literally making the choice without having to do any of the currying. It's doing a direct function call. So isn't that curious? I kind of wonder why that doesn't just... why it doesn't inline quite as well on the list comprehension, but perhaps that's the reason. Because of the way the list comprehensions work. So what that implies is that I might want something that does this kind of loop. Maybe not that one, sorry, number 2. This kind of loop. Oh, do we have a result? We have a result. Yeah, look at that. Total seconds, 116. This is the only significant difference because it both appear to be producing lists. 1,593 elements. Um, 1,000. There we go. 1,593 elements. The tip and tail are the same, so I'm going to presume that these two lists are identical in the C++ and Haskell versions. The Haskell version is being measured as faster, which is probably not completely real, but the fact that the C++ version, which is literally using no dynamic allocation at all except for the standard vector container, and the Haskell version are extremely close with my two primary versions that I'm interested in the Haskell side, sort of straddling the performance boundary. That is really interesting to me. In any case, what we could do, though, is we could have a version that looks like our best version here, but as an additional parameter, we could actually pass in the function by which we intend to do the filtering. I don't like doing, in this case I don't like doing that. Here's the thing. I like to be able to take sets of data and push them through, or even single elements of data, and push them through a series of transformations until they come out the other side as a transformed item. Filters, maps, whatever. Folds to get it down to an item, generators to get it out from an item, and so on. And I like doing that in stages. And it seems to me that the filter operation, in a sense, is a later stage. It's like, here's all the list of Pythagorean triples, or all the list of triples, actually, that are vaguely relevant. And then I want to filter them down so that they're usable by me, and then I want to use them. From a performance characteristic, though, we don't want to add them to the list only to pull them out of the list later, and unless your compiler is smart enough to tie the two together and find out that they don't have to do one and then undo it, which the compiler can't work through deeply enough in order to do it like this. You have to have the generation tied to the filtering to do it faster up front. In the case where the number of things you're actually accepting are vanishingly small. Just don't produce the element in the first place is always the best option, right? So, what I could do, for example, is I could have a version that looks like this, that still has to that has a different way of doing the filtering, like have the filter pulled out from the outside to the outside and passed in as an operation. So let's try that version. So we are going to copy this because this is our best version so far. Okay. We're going to make reuse of that filtered tries. So so the first thing that we want to do is we want to do this, and what we want to do is instead of using this, we want to say, and I don't think it should make a lot of difference, filtered try, try filter try, then add it to the list. So let's see what happens when we make this change, because this is now using that external try filter function, but it's that try filter function first of all is a global. So we're going to start there, and we are going to I am getting caught up in the performance characteristics of this, and is this relevant to what I want to do? Not really. I could find all sorts of interesting ways to adapt and massage this, but this is mostly satisfying my own personal interest in the performance characteristics between the two. And the fact of the matter is we have a couple of different variations which are in vague proximity of performance. We could find, the only thing that I'm curious on doing is how I would make maybe that as fast as the other one, and I'm not sure I can because of the way that it's probably passing in that curried function. So this is effectively the answer I was after. Number 4 is the one that I was after in terms of this is how you would implement it in a more Haskell-y fashion. And it's pretty performant. None of this involves none of this actually involves using any sort of functions that are pre-written, that are like low-level written by somebody else in C or something, except arguably how the list comprehensions implicitly work. But the act of building this up is essentially compiled code. The act of calling try filter and then the code that try filter has on the other side of it is all our written code. It's not like the operational behavior of this is being handled by handwritten functions that are in another language. In fact, almost all of the important functions, I think, in Haskell are written in Haskell. There are a few that probably have to be written at a low level, but it's not like, for example, Python, where you can get a great performance out of Python under quite a wide variety of circumstances when you can use Python's built-in functions to do the operations for you. Like if you wanted to turn a list of one thing into a list of another by mapping across a function, The thing that you would want to write would be the mapping operation and provide it to Python's built-in, mapping facilities, because the act of doing the mapping is itself probably not written in Python. It's probably written in a lower-level language. And then the only thing that quote operates slowly is the transformation operation, but not all the looping. And what you would not want to do is write map itself in Python as an interpreted operation. In Haskell, that's not the case. Map is written in Haskell, as is filter and all of those other transformation functions. It's a minor quibble from the point of view that who cares? It's a built-in function. Use it anyway. No argument here. In fact, that's why Python's used in a number of production facilities, even when performance is required for like single-threaded stuff anyway. So no argument from me. That may be a distinction that doesn't matter. But what it also means is that you are, in principle, capable of writing in Haskell fairly performant stuff. One of the examples of that is as above, where I unrolled these loops because I did a very C-like implementation, except I did explicit recursion, and it did pretty well. This is not okay. It's not great Haskell from a pretty syntax point of view, but it's workable Haskell and it's pure. This is a pure operation. It doesn't require mutation. It's very functional. This would actually be what I would do second rather than first if I needed performance, and I might even go deeper if I wanted to by experimenting with how the parameters are being passed around, because I'm passing around a lot of extra parameters. So I'm going to stop. This is where I would get to for solving this problem. This plus the functions as calls. That's literally it. Without changing the algorithm itself. All right? So next up, the next thing that I'm going to do, this has been a long ramble. This is totally not a tutorial kind of thing. This is a vlog, if you like. This is me thinking on the fly and solving these problems in an interesting way and trying to give some insight into how these languages differ. I like this solution. I think this is a pretty cool solution. There are definitely other ways to do this kind of thing, but lots of interesting things with using lists as a multi-valued solution to an operation, and there's all sorts of clever stuff you can do with that. Not necessary here, so I'm not going to rewrite all of this other code because it's all support code. So what I'm going to do next, I think, is to go over to the C++ side and see if I can trim this down in some other way. It's going to be hard to get it as nicely pretty as this. And now that I come to think of it, this isn't a problem space that was necessarily that was well suited to that, because it boiled down to essentially this. And this is more or less what the C program is doing. It just happens to be in a terser syntax, and even that isn't really all that important. I thought I was going to do more filters and maps and other things, but because we're only using a very tiny fraction of the solution space, I don't need to look at a value in a list generate a huge list and then filter it out after the fact. There's nothing really cleverer I can do in C++ than it is already doing. It's a very natural implementation. I could pass in the filter function from the outside, and I could do that in C++ just as easily as I could do it here, but that wouldn't really improve the solution all that much. So I think I might actually be, am I done with this series? What else can I do to the C++ side? So pilot by nested loops. So actually, realistically, this is no longer pilot list by nested loops, is it? All right, so let's actually relabel this. This is actually pilist by list comprehension. Yeah. Interesting. The real solution to this ultimately ended up being don't add it to the list in the first place. And of course, more interestingly, uh, lazily building a list at the tail can actually be more efficient than non-lazily, I guess, building it at the tip, but then having to reverse it at the end because that's an extra additional painful operation. Um, Curious, very curious that it behaves the way it does. Somewhat more shockingly, that the list version of this that I developed there, and it's clearly doing lists, it seems to be as performant as the C++ version, literally pushing things into a vector. Um, I guess the reason for that is the bulk of the code is actually not spent adding items to the collection. The number of items in the collection is not really that huge. And a lot of it has to do with how it basically evaluates whether or not it goes into the collection in the first place. Still, um, pretty cool that Haskell can generate the elements of those lists and either eliminate their construction entirely, and I'd be gobsmacked if it was capable of doing that. I would have to look at the underlying code to find out if that's the case. Or it's generating elements so fast that it's not really any worse than the overhead that C++ is using to keep expanding the array. And the number of times it has to expand the array, the vector, is not a great number of times. I do get obsessed about this stuff. It's very strange. It's very interesting to me that you can get that you can come at it from two different approaches and get very similar results. Very different approaches. So, well, except it's not really. When you look at this, right? Take a look at that. That is literally just more or less under the hood spinning in a loop. And the best version that I have, the faster version I have upstairs, is spinning in a brain not functioning. Is in fact spinning in a loop more explicitly with recursion. So there you go. You can do loops in either version of this. It just expresses itself differently in the language, and then you can get nice stuff like this. I'd actually like to see a version of list comprehension at the value level, at the runtime level, where I can state code like this and say, I want to build a thing, a container, and I can say whether or not it's a standard vector or an array or a list, and build it for me, and provide some syntax that says, here's how you build a single thing. So I can stuff, with the exception of the fact that I just try later, I can actually stuff that at the beginning. You can just put all that in here if you need to. Yeah. Yeah. I'd like to see that. I'd like to be able to specify how to build a vector like this. Now you can't quite do list comprehensions exactly. You can, using some template wizardry if it's fixed items, because you can use some clever parameter pack expansion and the like to be able to create lists. But it's nothing quite this convenient. And this allows for runtime quantities, so that like n can come in from the outside, and which is something you can't do with the template metaprogramming stuff. You can't refer to runtime quantities with the template metaprogramming stuff in like expansions and the like, to my knowledge. All right. What can I do on the C++ side? Nothing for those lists. I was thinking of using some of the standard the standard template library stuff, but none of it is going to make it cleaner than that. The thing is, with ranges, you might be able to. And so maybe what I'll do is I'll put this down and I'll go start thinking about how I want to do express this in ranges. Because part of the problem is, like, I can't generate a list of values for C. I can't generate a list of values for C like I can here, and then have them lazily consumed in order to produce part of this value. I have to express that as an explicit for loop because I need to be able to pull out one from here and then do all of this. I need to pull out one from here and then do all of this, and that kind of lazy pulling out of values from a list comprehension, or in fact from lists generally. You can't do that from a collection in C++ until ranges come along, and then you can basically have views which can be abstractly seen as being sort of lazy collections. Kind of like what link does, right? Ranges is C++'s sort of answer to link in a sense. And with that, I could do something maybe not quite this terse, but I could do something that was somewhat similar. Nothing about the standard template library that I can think of right now would actually improve this code, because this code is so simple. Right? I mean, I can't think of anything. Doesn't mean it doesn't exist. And I sure love to know if anybody has an opinion on that. C++, algorithm, header. So that, pulling up that gives me finds, searches, permutations, generate values for range with a function. Or generate n. What can we do with the generators? The generators take an output iterator, a size n, and a generator function, which has to be written in a specific manner. And this was actually all the way back in C++ 11. Generator functions like this are a little bit like the enumerable iterators in C#, except that they're not lazy. Say generator function is called with no arguments and returns some value of a type convertible to those pointed by the iterators. Okay. All right, let me think about that then. So basically the thing that's nice about this is implicitly what we have is this is coming up with a set of 3 values before we even start all of this. It's then building a try out of it. It's then testing the try, and then it's adding it to the list, provided that the try filter test passes. So this is the generating operation. This is the value that we're inserting. All right, let's try that. And in fact, we're going to do this. We're going to do this now before the stream's over, because why not? So PyList by nested loops is this. We're going to do PyList by so there's generate n and there's generate. I don't think I've actually, I may have used this once before in some code. There's some neat stuff in standard algorithm, like set union, set difference, the min-max element stuff, obviously, stuff to make heaps, lexicographic, compare and next and previous permutation, equal ranges, stable sorts. There's all sorts of neat stuff in here. But what we're talking about is effectively a generator. So So generate takes a first and a last iterator for an input. Hang on, I just want to double check to see if I understand how this is being read here. Generate takes first a forward iterator first, a forward iterator last, and a gen. And forward iterators to the first initial positions in a sequence. The range affected is first last, and it contains all elements between first and last, including the element pointed to by first, etc., etc. Okay. It assigns the value returned by successful calls to gen in the element of the range, and the generator is called with no arguments. So the problem is it has to be a blob. The generate has to be a blob. The problem with generate is I need to know up front how many elements to generate, and that's a problem. Because in the first case, I have a pair of iterators which dictate the size of what I'm doing. And in the second case, what I have is it generates a certain number of elements and it puts it into some sort of output iterator. But I need to know how many elements to actually use. So it's not actually that helpful to use the standard generate operation to do this. What I really need is a generate until some condition is true about the generator, or generate until the generator says there are no more elements. And that's not what this does, and I don't think there's a function in here that does that, because clearly what I don't want to do, like in the Haskell version, if I were to only look at this piece, this has a very defined number of elements. But if I don't know what this function over here does, then effectively the number of elements that comes out in filtered tries could be any number of elements at all. The size of that list could be anything. I could change the filter arbitrarily to something else, all the ones that have B that with a value that's divisible by 5, for example, and it would produce a different list. So I don't know what the number is ahead of time unless I had a formula that involved the numbers that were going into this operation somehow. And so I can't reproduce with generate, I don't think, this kind of behavior. Now, what I can do is have a generate function that I call that does this piece, which could be interesting, actually. That iterates over this piece and then applies a filter. It doesn't apply a filter. I would apply the filter myself. What I need is I need a way to ask the generator whether or not it's done. And this is something ranges would definitely help with, I think, because you probably have things like a take while or whatever where I iterate across a list and filter stuff out. Except that's what I was doing earlier on with the filter operations in the Haskell side. I'm going to get something running on the Haskell side, incidentally, just because I'm now curious as to how long it'll really take. So the one that didn't work very well, this one, where I was generating the right lists, but I was deferring operations on, deferring examining which element I was using until the filter itself probably couldn't see past any of this. I wonder if the filter could see past this. instead of putting the filter here, what would happen if I did? This should actually make it worse. So this would be the unfiltered tries. Okay. But then I'm going to do filter tries equals so it's going to be try filter. Let's just put that back in that way because it's silly not to try filter try. It's not really significantly going to change the performance of any of these, I don't think. Mostly I'm kind of curious to see whether or not I confuse. You see, I'm right back into exploring some of the performance characteristics of this by way of the list fusion and various kinds of other tricks. Equals filter, try filter, unfiltered tries. It's basically this. Add another one of these. I am insane. Insane in the brain pan. I am highly curious. I don't know why. I do not know why. I am curious about what will happen because it doesn't. I don't use Haskell for production stuff, so it doesn't really matter to me if it actually, is highly performant. Although it might encourage me to do so. I know it's used in commercial situations where the performance is important. Don't get me wrong. I am fully aware that this is actually used in production places, which is kind of cool. Did I get all of those? No, I did not, because it is not finding. Because it's not finding. That's why. This is by list comprehension. I want to make sure that I relabel these. It's not finding these because it's being case sensitive, which is fine, but now it's a bit of a problem. So this is by list comprehension 2. All right, so we still have number 2 running. Let's just make sure that nothing has changed as a result of this operation. Hey, you're coding, nice. Hey, Jarek. Yeah, I am. Sorry, Jarek. Well, no, that is not right. Oh no, that's just the. It's not what I meant to do. Hang on. Stack build. Did I accidentally change this to the wrong? Perhaps you meant unfiltered tries. Okay, yes, probably. This is probably not your ballywick, but I'm happy to have your company because I actually appreciate having somebody to speak to when I do this, even if they're not really that interested in the topic. Here we go. I am going to attempt to see whether or not it matters, whether or not these lists can effectively be fused away, because I'm kind of curious. So, filtered tries on 118. Why am I missing something? Because filtered tries is this guy. It's this last one. Yes, that is what I'm actually after. Let's try that again. Such a silly way to do this, but that's the way it goes. Okay, so I'm not actually running by list comprehension 2. I'm running by the loops earlier, the one that I did earlier. I just want to verify that my changing to use that external filter function that I factored out has not changed the performance basis for that. While I'm doing that, I'm starting to think it might be interesting. Instead of doing PyList by nested loops, we're going to do actually PyList by I guess by generator, except that I'm not actually going to use standard generator because the one in the standard template library does not have a fail condition on generation. What I really want is something like Haskell's unfold function, which basically takes a seed value, runs a function that generates outward into a series of values and just stores them, because that would be the closest equivalent. So there's my task. I've given myself my task. This is PyList by generator, but I'm not going to, I'm going to, let me see what I'm going to do here. I'm not going to have the generator return. Can I have the generator return when it ends? That means it needs to know when the start and ends occur, but that's probably what I want. So what I need is sort of a conditional generator, right? So I'm going to call this PyList by conditional generator, and effectively what this is it's like an iterator that it's like a lot of iterators in languages where you don't have to have an end. You basically just tell it go next, go next, go next, or whatever, rather than having to have a start and an end iterator. And you always test to see whether or not either next return to null, to see whether it stops, or there's some other mechanism to test whether or not it's ended, rather than comparing two iterators together, because I don't have an iterator to compare to. The idea of using pairs of iterators in C++ to me was always a mistake in the standard iterator. Actually, that's not true. When I originally started learning the STL, I thought it was actually really clever. But having used languages where they don't have it, and especially having used things like LINQ and Haskell with its lazy lists, I actually prefer the notion of not having two iterators but just one, because it means that you can chain effectively the result of one container processing operation into another more easily. It's really hard to do that with a pair of iterators. It's far easier when you only have one, which is why Haskell uses lists as sort of an intermediary for an awful lot of other mechanisms that sequentialize processing of elements, or searching processes of elements. So we're going to have a conditional generator, and we're going to keep this really lean because. So we're actually going to make this a struct because I don't really care all that much. And we're not going to try to make this generic because it's just going to be too much headache to like templateized this and all that. So this is going to be PyList by conditional generator. This is going to be triple. We're actually going to be even more explicit about this. We're going to call this Py triples conditional generator, and I could totally make this as like a more abstract, templated thing with lots of templated provided stuff, templated provided elements that would totally boil this down into exactly the same code at compile time for performance. Maybe I'll do that as an exercise later. Kind of not wanting to do it now because that'll take way too long to work out. But the basis of it will be something like this. It will be that we're going to have. Really hate that style of bracing unless I have to. Don't know why. But I did get used to it in C# and a lot of stuff because of LINQ. Int A, int B, int C. Actually, the starting values for this are going to be 1, 1, and 1. And we are going to we need to make sure, do these need to be long longs? No, they do not. Okay, because we've got ints everywhere else anyway. So we are going to have effectively I could either do it so that I call a next and I get back a value, but I also get back whether or not there's another one. I could get back so that I return an optional, so that I know whether or not there's any values left. Or I could return I could have a separate function that I can call that says, are there any more elements, or is this empty? The problem with that is then I have to store that additional state in here, because I would have to make that call, are there more values? Might I have to store extra state? Is that a thing I can avoid? What do I want to do here? No, you know what? I'm going to treat this as if it's a virtual list. That's what I'm going to do. I'm going to treat it a little bit like I have what is essentially an unknown length list of a particular type. That is lazy in its knowledge of whether or not it has an additional element until you ask for it. That's kind of the way a lot of C++ iterator stuff works. You test first to see whether or not, like, your current iterator is end, and if it isn't, you can do stuff effectively. And I could probably do clever things. Like, I'm not going to get clever. I'm not going to get quite that clever. All right, so what we're going to do is, that's our state. And we are going to have we're going to need optional, because that is definitely a very C++-esque way to solve this, especially lately. Instead of using -1 as an end case or null as an end case, because this isn't going to have null quantities. We're literally going to be passing back a tuple of values that is like a flat value, no references, no pointers, none of that stuff. So we are going to do optional, which means back down here we are going to do how is this running? Okay, so that did not affect, back to the Haskell just for a sec, that did not affect using the external try filter function did not affect our previous best loop that's up here. We are now going to run, we already know how fast this one runs. It's about 135 seconds. This one is using the post filtering like the slow one did, but I'm wondering if that post filtering can actually see through this list comprehension and push the filter down into the code that this generates, that this list comprehension generates, because this is just syntactic sugar for something more elaborate. So it would be interesting to see if this can push, the compiler can push this through here because of all the language rewrite rules, which this can do, which is really hard to do in something like C# or C++. So let's try that out. We're going to go to down to here. Nope, we're not calling it anywhere apparently. Let's go and fix that. There we go. We need effectively that. Right. Must fix timing code at some point. Probably not going to do that now. It involves a lot of forcing of values. Lazy values without actually needing the values in a list. I really wish I knew why the compiler's :print function wasn't behaving the way I expected. Oh, that was a little bit weird. Okay, so that's been built, and so let's go and do a run of that. And now we're going to go back to here. So we're back in the C++, and we're going to do basically what amounts to standard optional of standard. So we're going to need we want a val. We're going to do this. This is how we're going to make sure that nobody has to see the ugly inside, or at least less of it. Using what does the standard template library have as the? It used to have an internal type that that you could use to describe what the contained value was. I think it's value type. I think that's what it is. So I'm gonna mimic that. It's less necessary nowadays because you can actually ask information about the container's output, you can ask a container what, for example, an array index or asking for the first element's type is through other means. But I actually like this mechanism because as long as you're consistent about the naming convention, everybody can use it at compile time. So we're going to call this std tuple int. Totally not going to abstract that away. So standard optional value type. We could totally abstract this in a way that would be as performant and make this function fairly general, I think. But we're not gonna. So that is going to be next. We're just gonna call it next or get next. Never did like next. That to me seems that it doesn't return a value necessarily. So this is going to return a value, and we are going to write some code here, and hopefully we can get this inline. So we're just going to stuff it right into the class here. Don't like doing that for super long functions in C++ anyway. Although I've kind of gotten used to it in C# because it doesn't imply inline in there, but it does tend to clutter up the class. Okay, so this is get next. It can't be const. It might be able to be const expert actually, because you could potentially use this particular one. Might not be able to do that for every kind of conditional generator, but you can for this one. So I'm going to leave that in there. So that implies that you could actually use this kind of value at compile time rather than just at runtime, which is kind of cool. Might have some value. Not really. Not for this. So get next. What am I going to do here? I am going to say I basically have to have a little state machine that manipulates these values in the same way that these loops operate. This is super easy to read though. And so the only reason to do, at least it's super easy to read for this many loops. It's hard to think of this getting cleaner. And I'm certainly not going to make it cleaner with what I'm about to do. But the reason why you might do it this way is because this technique may generalize better to other situations. So let's give that a go anyway and see where that leads us, right? Because that's part of what this exploration is. Did that actually finish? 135 seconds. Okay, so actually, check that action out. Hang on, we got to go back to the Haskell for a second. This list comprehension, it was slower than our best, but it was I think the same as our previous list comprehension timing. Pretty sure. I'm going to test that in a minute, but it was faster than this one. PyList by this one was our bastard child. This one was number 3, which was was not that one. It was this one where we did have the explicit loops to produce the lists in question, just like we did with the list comprehension version. This actually produces the tries individually in a list, all of them, and then post filters them. Produces more than it needs and then post filters. Let's rerun 3 to see if we can even get there. Because effectively, since this is the same as our list comprehension, I'm even going to do a split screen here because I can do that. Since that whole little chunk of code, I'm going to risk expanding that downward. I think on the stream you can still see that. I'm following the stream, but it's obviously lagged for me. Yeah, okay, there we go. So this whole chunk of code is equivalent literally to nothing that I can see down there because I'm in the wrong chunk of code. It's equivalent to this. It's literally equivalent to this right here, actually. One line of code replaces all of that grunge because that's what you do with syntactic sugar. This is something you want to do. You want to be able to generate lists using sort of iterable source quantities, and that replaces having to do manual recursion. That's great. Love it. And can't have for loops because can't mutate index variables. So this works, but we had the problem where it seemed to be slow because we generated all the tries and we only picked out a very few of them. That's where we stalled on that. That's why this was the bastard child, right? But we just ran this, and it actually behaved like the one where we were doing the filtering way down deep in the loops. Fascinating. It means the compiler is in principle pushing this filter inside this list comprehension. Now it's not faster than the one that has the filter built into the list comprehension. Still kind of intriguing though. So let's run for this. Let's run number 3 again and see if that so-called bastard child really is as slow as I remember, or whether or not I was fooling myself, because that could quite easily be. So just because I'm kind of curious and obsessive about that performance characteristic changing the way it is, we just run that in the background because it takes one line of change, and we're just going to rerun it. And we can ignore it. All right, so that's on the way. Let's re-expand that back up. That's not quite what I wanted to do. Is that what I wanted to do? That is what I wanted to do. Just gotta move that back up to about there. Okay. So that I don't type and get all my text hidden. Yay! Onward, this generator. We need to be able to do a little bit of a state machine that updates this in a way that is consistent with that triple for loop. And there's ways to there are ways to abstract this too. I've often thought about some interesting ways in C++ to be able to turn different layers of for loops, to be able to compose them, like to be able to nest them without writing explicit nesting code. I'm not sure if that's even possible, but it would be nice to generate the state machine like what I'm doing now from for loops that you're explicitly doing. I wonder if you could... Not sure. I have to think about that. C++'s natural environment is not lazy, or C# for that matter, except for Link. Do love me a little Link. I'm looking forward to C++ ranges. All right, I've been saying that all stream, so... Okay, so here's what we're going to do. We are actually going to, every time we do a get next, we're actually going to do, I need to be able to cheat a little bit here because I don't want a am I in the start state. So what I'm going to do is I'm actually going to say in get next, we need a seed value. We could have, if I were doing this in Haskell, the unfold function takes a seed, a generator, it takes a seed and a generator function and produces effectively a list that only terminates when one of the values returns what is effectively an optional. It returns a maybe. It returns a maybe of some type, which is effectively exactly what a standard optional is in C++. So this is equivalent to our Haskell maybe, except that because it's actually producing a list and it's not just a thunk like this that produces an individual element. I don't want to have to store whether or not I am in my initialized state with a separate flag. So I can cheat. I mean, I have the control over whether or not I do that, so it's not a big deal. I can cheat though, and I can pretend that C starts at 0, so that when I increment C for the first time and all subsequent times, I actually get a value that I'm willing to start out with. And I don't have to worry about A and B because I can assume they are already okay. So I'm going to increment C, and if I say that if I need to know what n is to make all of this work. So that has to be stored as a parameter on construction. So actually, with that in mind, then I need a constructor, and at this point it's starting to look like I would rather have a class. So just for the public-private thing. I mean, I could just make it this particular thing private because class and struct doesn't mean the same thing as in C#, but all right. So this is going to be the public bit. This is going to be the private bit. Guess I can move the next function up to here. This is going to have a one parameter constructor int n, which I'm going to initialize n and do nothing else. So and I'm not going to deal with the case where n is 0 because that's just nonsensical for this, and it's too much work to make it all bulletproof to that kind of thing. So we're going to do if c is, and we're going to follow the logic right down here. C is less than, it's going to be greater than n. If c is greater than n, we're actually going to have all of the conditions in which we would, no, we can't. Yeah, when c is bigger than n, when we've just incremented it too far, that is exactly the case where we can do an early return. Std, can I do a make optional? It's usually a thing. Yes, make optional. And among the values, I don't actually have to do this. I can actually do using, okay, so that's value type, and I'm going to have this called, I want the value type to be what's returned, and I want privately using container type equals, or optional type. I call it optional type. I'm gonna have to. No, it's gonna have to be public. I don't need to make it private. It's gonna have to be public anyway. Except it's not the value type. So that's what I'm doing wrong. Duh. It's not. The value type is not standard tuple. It's actually standard optional. I want to do this. I'm going to do this. I'm okay with this. Except this has to come after. This is equal to standard optional of this guy. I can live with that. Because that makes this easier. But it also makes this easier. Because I can just go basically this and use the new brace form of initialization. Because unfortunately, I don't think I can do. I might be able to do that, except doesn't that create a function? The parentheses that follow. There's always been this ambiguity in certain contexts where parentheses after an identifier might mean a zero parameter constructor call, or it might mean call a function. I think in this case I'm okay, but why not use the brace initialization? Because that's unambiguous. It's a value. So that returns a default value, and a default value for an optional is the equivalent of Haskell's nothing, part of the maybe, for the tag, sort of tagged enumeration. So that's the only condition where that's going to happen for this particular generator. Other than that, what we have is, and actually, hang on, I've done something wrong here. I don't want to increase C first. I want to increase. Oh, okay. I need C to update the slowest. Hate having to write these state machines, which is why I like to generate it from like templated code. We need to increment A first. So if we increment A is allowed to get as big as B. So if so we're gonna defer that. So if A is greater than B, then b is equal to, increment b, and a is equal to 1. I could do this clever with some tuple unpacking maybe, but no, I'm not going to get, no, it's not, there's no point. It's not going to read any clearer. So we are going to go with if b is greater than, b is not allowed to equal c in all of the code that we've written so far. So I'm going to stay consistent with that. If this happens, then this is only, so this is going to happen once a has already been restored to 1, because the only way that this principle should ever happen is if it has come through here. So a will already be 1. So b is equal to 1. And we're going to increment c. Having done that, if c is greater than n, then we return optional value type. Otherwise, and actually we can reduce this. Return prefer using value-based conditionals in a lot of this stuff instead of imperative-based conditionals, which is kind of an impetus to maybe rewrite this in a value sense instead of a do things sense. But that's just my sensibility. So otherwise, std make optional. And in here we can go std make optional. No instance matches the argument. Let's say I'm about to do that. We're then going to do, we need to do a value type of A, B, C. Look at that. That's pretty sexy. So let's make sure this starts up correctly. Based on the initial conditions, because I don't think it will. So this actually, I want to start out there. And actually, we have to start out, if we want to start out in a legal state, which we always should start out in unless we have some like initialization bool or something, this is the first condition that's actually legal. Except that we want to make sure that the very first time we come into this, we're 1 away from being legal. So actually what we want to do is this. Now this is terrible. This is not a general purpose thing, but we're doing this because we don't have a seed mechanic in this. What we really should do is properly have a mechanism where the thing that we're doing can produce seed value as its first item, and the seed value is passed in, and then from that point on it does its work. But it is its own seed item, but it has to survive that increment. And that increment goes from technically an illegal value for the very first time it ever operates and becomes a legal value. So we can get away with this particular generator. It's self-seeding. And I'm okay with that for this because I'm not trying to be general about this. Okay, I think that will build. No, it will not. But it's because bi-nested loops already has a body. And we need the conditional generator to be above that. No. Oh, I just cloned it twice. I literally cloned it twice. Yeah, I don't know why I did that. I was in the middle of doing it, and I guess I did it again. Const exter implies it can't result in a constant expression. It implies it cannot result in a constant expression. Probably because make optional isn't const expert capable. All right, let's check this out. std optional const expert. Const expert standard optional possible implementation. Try to implement standard optional with const expert support as a practice. The usage will be something like blah. I don't think it is, and I would have to look it up. Lots of fun code out there showing how to build standard optional from scratch, incidentally. That's a neat exercise. You really want to learn your template stuff. That's an interesting place to start. Really hard to make super general, though. Which is why compiler writers probably get paid a lot of money. At least I hope they do. least I hope the ones that produce good compilers do. At the commercial level, anyway. I'm sure there's a labor of love exercise in there too, because it's kind of stuff I love monkeying with. No, some const expert. So, well, this should be const expert 2 if it's even remotely possible to do so. But cannot result in a constant expression. Optional value type is standard optional value type, and tuple should also be const expert capable. I'm gonna have to think about that because I love making things able to be used by the compiler, but it's beyond the scope of what I actually want to do in this particular video. So we're going to skip that because that's just my personal ballywick, and it doesn't have anything to do with this. So there's our get next state machine. This doesn't involve the nested loops, but it clearly should produce the same sequence of values, or that's my claim. So let's do this by conditional generator. We are going to take all of this out. We're going to say basically we've got our tries collection. We're going to create one of these. Auto gen, or G, I'm just going to call it G, auto G equals pi-triple generator, and we're going to give the size, which is n, yay, and we can see that it is in fact the correct type, and we can say, now we can do new C++ syntax here, I think, where we can do while auto tup is equal to, and I'm going to do const because it's not, you can const correct everywhere you reasonably can. Did I actually constify this as this? So this is returning a value, so I don't have to worry about its constness. So const auto tup equals g dot get next. Now this is something you can't do in earlier versions of C++, and I'm not even sure I can do it in this one. Doesn't look like it's complaining though. Where this is rare. You can do this in for loops, obviously, because you do stuff like this here. You haven't been able to do that in while and do loops, and it's or at least while loops, until fairly recently. And what this does is exactly what it does down here. It enables you to initialize something that's in the while loop, but it enables you to do that so that its scope is only in the while loop. So while this is true, I think I can do. Can I do this top dot? No, it's g dot. No. We want to return. We want to test top dot. What is the has value portion of the standard optional? I haven't used this in a while. Do. I need. Boy, this is weirdly unhelpful. I should have a list of functions available for what I can actually call in this thing, and my standard go-to place does not have what I want. Initializing. Okay, if other contains, I need to be able to see. Oh, let's cheat because I I can't find it visibly where I thought I was going to find it. So we're going to do this. Go to definition of standard optional, please. So a lot of constructor garbage that I don't need to know about. Assignment. Lots of template wizardry that you really, really never want to see. Wow, that is totally not helpful in any way. All right. I mean, I could probably parse it out if I thought about it long enough, but that is not going to be helpful. So, standard optional. Been a long time, so. Very, very straightforwardly, actually. I'm being thick. There is a cast from any optional type to bool. You simply test it. Neat, huh? Which actually is exactly why this works. That's actually really clever. Because what this does is it does the assignment. I'm pretty sure there's a semicolon syntax I can use. I think I can do something like this. Is that going to complain? Or do I have to use a comma? I might have to use a comma. No. I have to figure that out. C++ while loop initializer. Yeah, it is actually something you can do. So you can actually have, you can actually do something like this in C++ 17, I believe, and this is saying expected a. That is a little bit surprising. I thought I could actually do. Might be only coming along in C++ 20, that particular version of the syntax. But this is enough to get me by. And so I'm not going to push that point either. That's just, again, my own personal curiosity as to the language syntax. So let's skip over that. This gives me what I want because this is going to initialize this. It's only going to be in scope inside the loop, which is what I want. And as a consequence of doing this, tup actually gets tested as a truth quantity. So, which then, when it fails, it just falls out of the loop. So at this point, we can now do this. We can say, and actually, maybe what I really want to do, no, tup has to be the optional. So what we can do is we can do, we have to do something like, we could do actually, auto ABC equals tup. All right, how do I actually get the value out of the optional? Again, haven't done this in a while. Good God. I am getting rusty. So what I kind of want to be able to do is I want to be able to pull, there's a couple of layers of this that I could do. This is not going to work because it's not going to know how to break up that tuple. I think I actually have to do this. Is this not how I do this? Spec an identifier. No, I guess I have to do this in order to do structural binding. I'm going to do this in stages and see how I can copy it out. So what this really actually is it's actually going to be this guy's value type, t equals tup. Can that actually be done? No. Why? Because no suitable defined conversion exists, and it should be able to. So I still need to know how to pull that value out. Several ways to create it. Returning standard optional, don't care about that. Accessing a stored value. There's several options for accessing a stored value. Operators star and arrow work similar to iterators. So it's so the optionality of this becomes a pseudo pointer, which is an interesting choice. But I guess because it's a value type, it's technically they don't define dots and arrows typically as overloaded operators. So why not reuse it, right? It's just a way to say extract the value. So that's that. That actually, the type of star tup is actually the value type internally. So actually what I can do is this. And actually more importantly what I can do is this. And then more importantly what I can do is that. So there we go. I do have to, oh, is that not actually going to work? Auto can't deduce references, possibly an unintended copy is being made. Oh, that's really annoying. It's not going to let me do this, is it? So if I actually back all the way up to here, it still doesn't like that unless I do... Interesting. All right, so what I'm going to need to know is C++ structured binding. Love this in C#, love it just as much in C++. I'm glad they added that as a mechanism. Binding to a tuple, binding to an array. So we've got various kinds of bindings. Binding to an array. So this is pulling out a concrete value t. This is saying auto doesn't deduce references. A possible unintended copy is being made. What is the potential fix? But we know what t is. T is effectively the value type of high conditional generator. We already know what this is. It's a tuple of ints. Oh, it's always fun when your type system messes with you. But the thing is, I actually appreciate the fact that it's being type strict on me. I really appreciate that the linter that they got built into this thing is giving me an extra headache. So the problem is, it says this is it doesn't deduce references. A possible unintended copy is being made, and that's actually the case. I actually want it to make a copy. I guess I technically don't need to, because tup is actually, that's an interesting point. So this is a the comment it's making is actually a linter. It's actually a warning rather than a strict error, I believe, and I can probably prove that by trying to compile it. So it does compile, but the linter is warning that a possibly unintended copy is being made. And it's probably doing that because effectively T already exists, so I could actually bind A, B, and C by reference. And in fact, tup is already being made, so I could bind directly to the tup elements by reference. So what I want actually is auto-ref. And this gets rid of the problem, because now these variables are not going to live any longer than tup is, or even the internal portions of tup inside the optional. And in fact, I can make that const. I can get rid of that, and then I can make that const, which then copies it into try. So this avoids a copy. It just gives me references to the individual elements by structured decomposition. And in fact, these are going to end up being optimized away as just as labels into the interior bits of this. So that's going to be probably a no-op right there. It's probably not even going to produce the references. I would be surprised if it did, and it shouldn't. Because I'm immediately just copying them out into try as part of the try's constructor, and then I can do the rest of the work. So check that out. We now have a generator-based version of this. Now, I'm not going to claim this is actually going to be faster than that tightly written for loop, but it is intriguing, right? So let's see what happens when I actually run. Okay, I can get rid of this code now. Let's see. I need to do tries.pushback try in there, which I already have. So let's do this. So this has turned the nested triple loop into what is effectively a single loop, which does exactly as much testing on the try itself, and I suppose you could argue exactly as much state management, except that like this kind of technique could generalize to any kind of generator mechanism. I wish I could use std generate to do this, but std generate does not take a generator that conditionally succeeds or not in order to produce a list of arbitrary length. It has to be a fixed length thing. I find that more as the pity, but this kind of thing, made more general, could be the basis for what could be std conditional generate, for example. Why they didn't provide it, I don't know, because perfectly legitimate thing to want to do, and it would be the equivalent of the unfold operation in Haskell, and it may very well exist in C++ 20's ranges. Haven't looked, but we have compiled this, and now we have to actually make this. We have to make this code. We have to make this code do a thing. So we have these correctness functions which we wrote from the when we were setting everything up initially by the Haskell side. So so I need that conditional generator text. Where is it? This guy, by conditional generator is what I called it. Let's make this nice and pretty. Not pretty. Functioning. Really not pretty. So we want this guy. So this is going to be that. And this is going to be that. And then we're going to also do this. And I really should, yes, I know, for all the people watching this on YouTube long after the fact, I really should go and make all of these correctness and timing functions more general, but I just don't have the energy. Okay. So primary tests, I can add the correctness version to this, and I probably should, because I don't know if that state machine is going to work. Just once I'd like to test to make sure this is going to work. So I'm going to do pylist by conditional generator. Correctness, I'm also going to std cout. Can't type anymore. Okay, we have separation between the two things. That's fine. That's I'm gonna add another one there because to compensate for this short one. We're gonna go down here. We're gonna say by nested loops timing, put a separator, and then by conditional generator. Right. Sweet. We're going to temporarily drop this down to 1,000 elements, just so it completes in a reasonable period of time for all the operations. So let's build that, and let's see what happens when we run this sucker. Now I gotta watch the stream to make sure that the window pops up appropriately. It does, and you can see that we got the time tests are the only ones that ran. The values that came out seem to be the same and contain the same amount of elements, does it? Yes, 158 and 158, but I didn't run the correctness code. So let's quickly go back. I just want to be a little bit careful here. So as a unit test, let's, sort of a unit test, a whole unit test, let's actually run the primary tests, because I just want to make sure that we haven't introduced a bug somewhere insidious. Nope, everything passes, succeeded and succeeded, so those pass, but we don't want to be running those all the time. So it's correct, but that's fine. And because these are individually timed, I can just leave both of them running, except both of them are going to take about 130 seconds. So just to see what the performance characteristics look like. Okay, I will run both because they're internally timed, but debug, start without debugging, go. All right, so and that did not pop up on the stream. Where's the pity? Oh no, it did. Pull that out a little bit. Got to remember how OBS sees it is not the same way as what I see on screen. Makes things a little bit challenging. Kind of want to pull this down a little bit. I may have to shrink these from being a standard 25 lines to something shorter, just so that I can fit this all on one screen in a sensible manner. But right, so that's interesting. So once again, on the C++ side, what we have is, in the first case, 3 tightly written loops that all it does in the interior is does a filter operation. Did I actually have the filtering in there still? I just want to, now I'm getting paranoid. Yes, I did. So is right angle and has common factor, and actually did I do the other tests for zero, the zero values? I might not have. I might be doing more work on the Haskell side than I'm doing on the C++ side, so let's just go and check that. Has common factor, is right angle. No, those are the only two that I'm really doing. No, we're fine. We're fine. We're fine. Oh, let's go over onto the... Oh, so check that out. Remember, okay, I got to stop the C++ version of this because, interestingly enough, the Haskell version is never completed. So let's see what that meant. Let's quickly go back to the Haskell side. I got to kill that. On the Haskell side, very briefly, the bastard child version of this, number 3, it did this explicit looping, which was fine, and then did the because we did explicit looping in number 2, it was really fast. Explicit looping with recursion, perfectly fast. Did a add of each try, but only if it filtered, right? If it filtered, then it would add it, and if it didn't, it would just leave it off. It would then, and that worked really, really well. That was number 2. That was our best performer out of the lot of them, just by practical implementation. Don't really care about the numbers specifically, but the reason this is interesting is we did explicit loops in number 3, but we did all of the tries into the resulting list, and then afterward did a filter. Okay, so that didn't work very performantly because effectively it was adding all of these into an explicit list, which was quite a massive list. And then it was filtering them out after the fact. And even though it doesn't produce more elements than it needs, it only ever produces one element at a time, just like a generator does, it still had to look at the bad tries and throw them away, lose that to the garbage collector, I guess. I am guessing here a little bit, and then went on and processed the rest of them. So it was never using more memory than it needed to, but it did have to unpack this and throw it away. Unpack this and then generate a new one, unpack the next one that came along and throw it away. However, in principle, number 2 here, list comprehension 2, should have behaved the same way because we are literally producing every value possible, and then we're doing a post filter on it. So how come this post filter ran properly and this one didn't? And the reason for that is they're both correct because for a small number, for n, they both produce the same lists. Why is it that this one actually ran? Just to prove that it ran, let's just very quickly go and do this thing, because now I'm getting paranoid and I don't want to say something that isn't true. But I find this a fascinating behavior, and frankly, so should all of you. I find this fascinating because what was capable of happening here is both of the okay, I gotta start that up by doing a stack build. And I just want to make sure, doubly sure, that this is actually calling the right one. It is by list comprehension 2, by list comprehension 2. All of that behaves correctly. So let's go back in here. We're going to do a measured run of this. And I think it'll come back within a minute 35, sorry, a minute and a few, 135 seconds. That's a minute and 15, roughly. Why did this one work? Why did it work? We're clearly generating an infinite, not an infinite list. We're generating a monstrous list for n that's 10,000. That is absolutely a colossal list, and it's being produced just as lazily. I should be able to prove that a different way. I'm pretty sure, I'm confident in saying that this guy here is producing. This guy here is producing only, not that one. This one here is producing a finite list. Because it is it producing a finite list? Let me think about this. It is, when this returns, it is going to return the thunk, or the lazy operation of returning, for the non-zero case, is going to return a lazy thunk involving this. That lazy thunk involves basically evaluating, pulling out the first element of this, then producing the tail of this with this concatenation. It should be as lazy, and now I want to make darn sure of it. Because if it's not, then that's why that's failing. I'm pretty sure this is being lazily evaluated, though. And I may be able to prove that by copying this bit out. We're going to just produce debug underscore nested tries n equals, and then this big thing, which is basically that interior code, except I'm going to have to do the where bit, so I'm going to do all of this. But what I'm going to do is I'm actually going to return pylist cc1, and I'm going to reload this. So it ran at 135 seconds, so that's great. I know you're dying to know whether or not the C++ program worked, and I will get back there in just a minute. Stack build. And actually, I don't want to build. I actually want to go into stack GHCI for this. Pylist C1. So here we go. I'm going to build it, but I'm going to actually go into stack GHCI to be able to show that this is actually lazy. So it should be fairly obvious. I should be able to take, say, the first 100 elements out of that without it even blinking hard, because it'll be able to pull off the individual elements one by one, even if the total resulting list is massive, right? So stack GHCI. So here we go. Set prompt. I should make this a default for the stream one of these days. So there we go. So let's say that we had a really, really long list. Let's say we had what would be the best way to explain this? If we have a stupidly long list, like let QQ is equal to 1 to 1,000 million billion, right? That binds right away. It's not evaluating the list in any complicated way. So the question is, can I get at the first elements of this without without having to evaluate the whole list. Evaluating that whole list is going to be absolutely massive in order to be able to do it. It will just use up too much memory. So I should be able to do, for example, take 100 of QQ and bang, it all outputs, and QQ is no more evaluated than it was before. Except, well, the first 100 elements are. They should be explicitly stored. But the rest of it, the tail of that, is still an unevaluated thunk. So that's the same way that, for example, debug nested tries 5 it gives us all of these tries that are appropriate. I hope everybody can see that. So that we have basically 112 is the first valid one, 113, 114, or sorry, 123, 223, then 114, and so on, incrementally, just as we might expect. But if this is failing to generate a very smoothly, this is failing to generate a list that is as easy to pull out like that was, when given an initial quantity that's really huge, if it's somehow stalling because I generate a really big version of this, then that would be the bottleneck. And one way to test this, in principle, granted the interpreter doesn't work the same way the compiler does all the time. Let's try to let tries equal debug nested tries 1,000 million billion. Right? Why not, right? So let's do that. Well, okay, that binding doesn't do anything, but can we get out the first, say, 125 elements, which is what we printed out? Actually, it's not quite 125, but let's say the first 30 elements out of this without causing it to have to either generate the whole thing or run into some situation where we've got thunks, like inefficient thunks on top of thunks on top of thunks, which you can do if you try to keep appending to the tail end of a list a single element. If you try to append to a singly linked list, a single element over and over and over and over and over again. In C++, for example, it would be an O(n) squared operation. In Haskell, it would be O(n) squared to get all of them out, but it would definitely be O(n) operations in order to get the first element out, because it would have to at least evaluate in Haskell vertically to get all of those append operations pushed forward onto the second element. Is effectively how that works. So let's find out, because I don't actually know the answer here, because I may not actually understand what's going on in that function. So let's actually ask that question. So take 30 tries as fast as possible. That tries list is 1 billion elements long, but I only pulled out 30 elements. They are in the correct order. They are valid. And it did not do something extraordinarily funky where the act of trying to extract the first one had to do a bunch of extra work to push all those deferred thunks forward. That's usually what happens if you do weird appends in the wrong direction. Let me see if I can actually demonstrate this, because this is kind of telling. A little bit of education. So let QQ equals, and I'm going to use a fold operation, and I should tell you what a fold operation is, in case you don't know. Fold operations, fold left in this case is what I'm going to use. Fold left, you give it a seed, you give it a function like plus, and you give it a list like 1 to 100. And I have got the values in the wrong order because I'm a noob, apparently. So there we go, right order. It produces 1.100 to actually not mean a decimal value. 50-50, exactly correct. That's exactly what happens when you add the first 100 numbers. So what I'm going to do as a fold instead here is I'm actually going to fold with append. So I'm going to append one element to the end of each list. So I start out with the empty list. I'm going to give it a bunch of numbers. Actually what I'm going to do is I have to wrap each of these in an individual list. So I actually technically have to have like a list of 1, a list of 2, and so on, because append requires a list on the left and the right. So let's cancel that for a moment. And I'm going to talk about map. So I want to show an issue here. So this is going to be, we're going to map, say, +1 to a list of values. Standard map operation. We do this in the link all the time, for example. It's called select in LINQ. Love this. So this just applies a function to each element of the list and returns you a new list. It's a transform of one map to another. It doesn't even have to be the same type. I could do, for example, I'm going to write a little lambda here. I'm going to say, I'm going to get a V, and then I'm going to, from integral to make it into a double, I might have to do it's really hard to do casts in this. But what I can do is I can then say from integral and then plus 1.0, and that's going to default to a double, I think, which then makes the return type of from integral, so that should all work. And so this is turning a list of ints into a list of floats, and it fails because non-type variable in the constraint. Because why? Oh, because it's a function. I need to do that. There we go. So it doesn't even need to be the same type. So here's going back to our fold. Here's what we're going to do. So ignore that for the minute. If we do a map of take a value and then wrap it in a list, and then we give 1, 2, 3, 4, for example, that is exactly what you would expect to come out. This makes each value become it's a single element list that contains that value, right? So let's combine these two things. And I'll tell you why. It's because what I want to do is I want to do an append. So what I'm going to do, I'm going to fold with the intent to do an append. The starting list is going to be an append of an empty list, and but I need a list which is effectively I can do a list comprehension instead of doing a map. I'll do a map anyway. So gotta love being able to do list comprehensions to do a lot of things maps do. But anyway, so we're going to map that listify operation that you just saw. I could probably do this a better way, but it's not coming to me what the function that takes a value and returns a list containing a single element. That's got to be a section involving the colon operator, and I don't care because it's not important. So there we go. That map is going to turn each of these values into a list. So list containing 1, list containing 2, list containing 3, all those in a list. And then it's going to append each one of these to this. Now, this is what I was talking about, where if you append a single element to the end of a list repeatedly, it just builds up a huge number of deferrals, because in order to get the first value out, you have to find out what that first value out is, but push all of the deferrals that are all at the head, one element further on. And that's why laziness does not give you a way out of the fact that pushing an element to the end of the list repeatedly is an n squared operation for n being the number of elements. Same running time as in C++, it's just when the operation occurs. So if I do this fold, ultimately what I end up getting is the values in the correct order, because basically what happens is each of these values gets turned into a list. Each of these values then gets appended to a list by concatenating one list with another, which effectively pulls out the element from each of those individual lists. So all I get is a value from 1 to 100, the slowest way possible, because of all of those appends. So let's show that this is actually a problem. Let QQ equals, and I want all of that. Right. So there's that. So let's take this up 1,000 million. Did I type the right number of zeros? It's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a billion values. So that and in principle, I only want to take the first few elements. But unlike this list here, which is really simple to pull out the first, say, 10 elements, this list, QQ, is going to have built that list in the most inefficient way possible by doing repeated appends. Now, the binding doesn't take any time at all, because the binding is just, that whole function is just lazily evaluated. But if we force the value, we should see that it takes an awfully long time to even get the first few values out. So let's take 5 QQ, and this may break my program because I did say a billion, but let's find out what happens. And there it is. It's taking time. It's taking probably a lot of time. And you'd think, well, why? It's just the first 5 elements of a list like this, only longer, right? And if I had actually taken the first 5 lists of first 5 elements of this list, it would have found it would have been perfectly fine. In fact, I demonstrated that, I think, earlier. So what this effectively does is, and I'm going to actually kill that because otherwise it's just going to chew up memory and die horribly. What effectively this means is, if you build up a bunch of early thunks, if you build up a bunch of deferrals all at the head of a list, which this clearly does, you're going to have to work through those deferrals just to extract the first value. And that's why effectively doing an append like this repeatedly is bad. But it's also why, for example, debug nested tries does not exhibit this property. And the reason why this is the case is because the first thing that it returns is effectively this. But in order to get to, but what's going to happen is this may contain a list. Let's pretend that it just returns a list. This is going to be a tail list that is only going to get evaluated after all of the, after we've moved past all of this. None of the thunks are being built up on the head of this as a result, even after the recursion. The recursion here only applies to the tail. It doesn't apply to doing anything to the head. This recursion, in fact, only gets called after these are exhausted and not when these things are starting to be processed. So although it does have to basically partially evaluate this append in order to move past these, it doesn't have to do anything with any of the rest of this. That reasoning can be argued all the way back up this list. The practical upshot of all this, that's why this guy, that's why this guy actually operates with any kind of speed. So let's get back to the thing that's interesting. The thing that's interesting is, once again, this is effectively equivalent. Ignoring that whole issue, all I've shown is that the delay in number 3 is not as a result of this. The delay of this function is not as a result of this. This is lazily producing, at least I don't think it is. I'm pretty sure it isn't because we just copied this out. This is not causing the delay. This is producing values fairly efficiently in a list. However, this filter is happening after we generated this big long list. So even though it's lazily evaluated, I have to examine and throw away these elements that are already produced. That should be the case for this pair of functions, because this is just that same production of every try possible. And this is doing a post filter. So why does this run fast at all? And the reason must be that this filter operation, once this is turned either at the code rewrite level that Haskell does on the functions themselves, or at a lower level where it's doing the optimization, that filter operation is actually filtering to be inside the code that actually implements this this list comprehension. I find that fascinating. I find that an amazing optimization that I would not expect very many languages to be able to do. Because in a lot of cases, by the time we get to the optimization phase, we're long past the point at which you have information about the fact that this filter operation is doing the same thing to each individual item. Like, this can be pushed down in. I find that fascinating that it's able to do that. I'd love to know exactly the nature of that. I don't have time. I just wanted to go down that rabbit hole because it was a fascinating diversion. This is equivalent to the slow one above. Both of them work. This one's faster. In fact, this one is very nearly optimally fast. Like, word to the wise, try to use built-in things like list comprehensions, built-in generator functions, and built-in filters, built-in maps, all of that higher order stuff, because you're probably going to get some pretty cool behavior performance-wise without having to lift a finger. It's not always the case, so don't get cocky, but that's pretty cool. Anyway, back to the C++ thing, because that's where we actually were doing the most recent generator code, right? So this is a very Haskell-esque like thing to do, which is to lazily generate these things. We're generating them as we need them, and we're filtering them as we need them, and then adding them to the list as we need them. Let's run this at long last. So we're going to start without debugging, which should pop up the window, which I can move over to the side, but I want to make sure OBS is showing that as well. Should be, yes. I'm going to let that run for a few seconds while I go get some liquid, because I've been talking for 4 hours straight. Oh my goodness. This has been delightful. I'm going to stay on the stream. I'll just be back in a few minutes. So, what we see here in the C++ output is pretty much what we expected to see before. The elapsed time is 134 seconds, which I think is... oh, that's for the first output because we're running both of them. So we haven't seen the result of the second one yet. That's the expected output from the last one. That's about as fast as the Haskell version was. In fact, it's as fast as the Haskell version... well, our second best Haskell version one, the one that uses the list comprehensions, either version of it. What just happened? Did I lose the stream? I hope I didn't lose the stream. That was extremely weird. Okay. I'll bite, pull up the task manager, and see if I'm using an unreasonable amount of space. So maximum CPU usage on the current system is... view. I haven't had Process Explorer set up on this in quite some time. So organize columns, no, I don't know. How do I update the columns on this? Let's let that keep running for the moment. Select columns. Don't care about the company name. I might at some point, but I really don't care about the company name. The description is helpful. Oh, what the hell, I'll leave that in there. But what I really want is process performance. CPU usage should be in there. Curious. Why do I not see... Oh, there we are. It's just upside down. Pythagorean triples, that's okay. The private bytes it's using is only 696. So why is it taking an unreasonable amount of time? Have I borked this? Curious. Very curious. I might have to actually do step debugging on this to find out what's happened here. Oh, I see what's happened. For some reason, the tool chain has crashed on me. Isn't that fun? All right. So what I'm going to do is I'm going to so it's probably actually completely dead. So I'm going to do this. I'm going to kill the process, which means I probably have to kill that as well. And I'm going to reopen it. That was weird. That was seriously weird. So hopefully that's all coming back up now. All right, we're not going to crash Visual Studio by doing this that way again. We're just going to, I think I can start without debugging. I should be able to do that and just let it go. Time test start should show up, and did that show up on stream? We'll find out in a moment, otherwise I'll have to fiddle with OBS. It should. I'm going to check the Process Explorer just to make sure, monitor this thing just to make sure it's not doing anything dorky. It is using one core entirely. Its private bytes aren't rapidly going crazy, so it's not using up a stupid amount of memory. All right. Don't know what that was about. Do not know what that was about at all. That was extremely strange. So, looking through the code here for a moment, while I am waiting, I'm just going to double check that this isn't doing anything weird. So, this keeps evaluating as long as there is a next, and we know that it succeeded because when I ran it on 1,000 elements and I did the safety check, the unit test, it all ran and worked. So it shouldn't do anything supremely bizarre when it's running. Let's just double check our logic here, but I mean, if it failed, it should have failed earlier on the much smaller test if it was going to fail at all. And I'm only doing up to 10,000 anyway. Each of these ints never ever gets seriously high in the first place. So I think we're good. I think we should be good. But I also think my computer did something funky there, so let's see if that happens again. The actual amount of private bytes allocated actually, oddly enough, went down in my Process Explorer instead of up. Okay, so now it's running on the second stage because that one is the original. That's bi-nested loops, 125 seconds, roughly kind of what we expected. The Haskell one is about 135, I think, with the list comprehension version. But that includes startup time, so it's probably like 132 or something. A couple of seconds startup, maybe. Maybe. I don't actually know. But it is also timing the console output too, so Really have to fix that. Ooh, you know what? I can do that while I'm waiting. Why waste time? So in the time it function, what it does is it actually evaluates v between a start and stop. And we're getting a bogus value. We got one good value on our first attempt, but that was because the list was reversed. And basically the reason is when you evaluate a reversed list, it has to evaluate all the elements of the list. But when we're evaluating a non-reversed list, if this evaluate operation only evaluates v as a list to what's called weak head normal form, which is it makes sure that it has has a head available, or it's an empty list. But it doesn't have to evaluate. It makes sure it evaluates as a list, but it doesn't have to evaluate the individual elements, and it doesn't even have to evaluate the spine, the tail of the list. So this isn't sufficient for lists, and to make it sufficient for lists, I'm going to have to get clever, because what I want to do is I want to make sure that I only evaluate as far down as the initial element of the list. I want to do a shallow. I want to do an evaluation of the entire list, make sure every element is accounted for, but of the final resulting list, because I'm going to print it out anyway. And I want to evaluate the elements that are inside, but I don't want to go any deeper than that. So what we're going to do, what I want to do actually is I can collapse these eventually. This is kind of a silly thing that I have this duplicated. And what I'm going to do, you can't overload functions in Haskell except by way of making them part of a class, which is effectively an interface in other languages, for lack of a better way to describe it quickly. But you can't overload functions, so I'm going to call it time at list. I'm going to call it shallow list, I guess, because I don't want to evaluate super deeply into the elements. And if I want to do a deep list version, I can do that. But if we know that v is a list, so basically this is going to be time at SL. This has to be a list of some type A. That's how you do generics in Haskell, but it has to expressly be a list. It could be a list of lists, but it has to be at least a list. And what we're going to do is, if we have the V's, we're going to evaluate. We want to evaluate these. This isn't actually solving the problem because it's just renaming things. But what we're going to do is we're going to change evaluate this to be actually evaluate, and we are going to go and evaluate each of the individual values of the list, but that's also implicitly going to evaluate the spine, because that's how we get to the other elements of the list. So what we're going to do is we're going to evaluate, effectively map. We need to be able to. How do we do this? I need to be able to visit each element of the list and look at each element of the list and force its evaluations. So, evaluate will force the outer layer. So in forcing the outer layer, we're going to force we're going to evaluate. I could do something like evaluate last VS, because it's going to then get to the very last element, and it's going to evaluate the whole spine, but that's not going to evaluate the individual thunks in the middle. I'd like to know what it takes to evaluate those thunks as well. That is taking a lot longer than I thought it would for that second pass on the C++ function. That is curious. So the question is, of course, why, right? So we're going to kill that. We have to find out why. So skip this. We're going to come back to the time it thing later. We're going to go back to what is going on here. So we're going to have to run in debug mode. So, start it up. And actually, while we're doing this, let's go and eliminate starting up that first. I'm gonna eliminate that. Start it up, please. Now let's see. Can you see this? OBS may not agree. OBS does not agree. So we are going to open that up and say that you are watching the debug console for the moment. And I'm going to move that a little bit further out into the middle so you can see the whole thing in case it's relevant. So let's give this another, are we currently running? We are currently running. Okay, but we're not getting anywhere very, very far. So let's actually now throw a debug into this. I really wish I had a debugger this easy to use for Haskell. I don't yet. I should look for one. It's a little harder to use because since everything's deferred, you end up hopping all over the code as stuff evaluates, because that's usually how the debuggers work, which is interesting in its own right. All right, let's throw a thing in here. Are we ever getting into this code? Yes. Let's take a look at what the state of G is. It is getting there. It's just getting there very, very slowly. Okay. Tries has 119 elements in it so far. Okay. We're not getting stuck in a weird loop, are we? In order to be able to figure out if we are... I mean, we know this terminates. In fact, we can prove that by faking a situation where it succeeds. So for C, let's just make this 10,000, right? Let's just make it the value it has to be. So if C is greater than N, okay, so actually we need to make it 10,000 and say 1. So if we return the failing condition, we step out, but it still goes inside here. So why is that? Because we returned optional value type blank. Can we not do this test? Is this g.getNext? Okay, what is tup? Okay, let's do this again. So it's still producing a valid value. Hang on a second. B is greater than or equal to C, then plus plus C, but hang on. Let's get back inside here. But this should be, I mean, let's just make this stupidly big. It doesn't matter. Something stupidly big. Oh, it does fall out. So it does finally fall out if C gets large enough. So what does that imply for us? It implies that this is operating really, really slowly. So let's just throw a cheesy little bit of debug in here. See out. So when C is increased, let's actually print out a message, because that's going to go up the slowest of all. So, and we're going to be timing this, which we don't really want to do, but it's going to be outputting relatively infrequently. So. Yeah, okay, so this is getting slower and slower and slower, which is what we expect. So, writing a manual generator like this, bad idea. It's not terribly fast. Because that's not going to get to 10,000 anytime in the near future. And yet that triple for loop did just fine. Because it's super, super optimized by the compiler. Isn't that fascinating? Because this should actually be fairly tightly inlined. Because we want it to be. We want it to be super, super fast and inlined into the caller. We have to return an optional type as to whether or not we actually got a value out. That should be relatively efficient, but I'm guessing that it isn't. Because take a look at that. We need to get this thing all the way up to 10,000, and we're just crawling at this point. Now, granted, this is in debug mode. So let's actually go and, so that's not really fair. So let's actually go off into release mode. And let's see what happens when we do debug, start without debugging. Let's see how fast this thing is. More importantly, let's see what happens when C is getting way up into the thousands really fast. So this illustrates, I'm just going to quickly pop OBS back over to check that action out. We're going to get to 10,000 pretty quickly here. I don't know why it stalled. That is really weird that it stalled. It's not obvious to me that that should have happened. All right. Maybe it doesn't like doing one after the other, and I don't know why that would be the case because there shouldn't be any memory management issues related here. So let's take this output statement back out again, and let's just let it run. So odd. So this is only running the one test, that second test now. So in principle, yep, using one core pretty solidly. I'm having weird problems with my build chain today. $7:47. It shouldn't take it past 7 minutes 50. Wow, 5 hours. Yeah. Kind of curious. Int should be a 64-bit value. I wouldn't expect. No, all these values should be fine. No, Macheriki, it isn't a trivial amount of coding. I mean, So far, about 10 hours worth of just coding on stream here, and granted, some of it's been looking up stuff, and sometimes it's been going off on tangents, which doesn't involve coding, and sometimes it's just talking about the code. But it's, and a lot of it, at least some of it's duplicated, because I didn't spend a lot of time trying to tease out every way to, reuse code. But yeah, it's been kind of a fun exercise because I don't know. I have I'm finding that doing this for the sake of exploring something when I'm not sort of engaging somebody else in it is not doing it for me anymore. Um, some of this stuff it can be. I mean, it may only be fascinating to myself, but if I pretend that somebody else also gives a crap, it's fun to actually explore those things. Um, This is taking a fairly long time, and so it may be it's not using up outrageous amounts of memory, so it's not suddenly going off the rails to add too many elements to that list. Um, uh, but getting all the way through that implicit triple array may be taking longer than it can handle. The tight, because this should be equivalent to the tight loop here, but when in this code, this can be optimized down to to a crazy level because the compiler can literally see the 3 for loops right there. It knows what the bounds are. It can do all sorts of crazy substitutions, all sorts of neat optimizations to get that to work. Whereas in this one, all of the iterator state is buried inside of this this get next operation, and I did run it on 1,000 elements earlier, and it ran just fine. Maybe a little slower, whatever, but it did run just fine. The But I don't think it's able to optimize this away quite as much because this is hidden behind a return value which has a lot of complexity to it, wrapping it up in an optional. And so each time it goes through the loop, it may not be able to do the kinds of optimizations because it has this optional value sort of in the way. You have to be able to, in order to figure out how to do optimizations that might survive one pass to the next, seeing it in the for loop form, the compiler could study that as part of its syntax tree. Studying this is an implicit set of loops, and it's not going to see the equivalence, or it might not see the equivalence. The kinds of optimizations it can apply are probably not as clever. I like generator mechanisms like this, but generating a complicated type may be worth it. Generating individual for loop values for this implicit triple for loop may not be worth doing this way from a performance perspective. Now what I could do is I could try to get rid of the optional type and do this a different way where I'm not hiding it behind something that complex. And that is potentially reasonable. Optional is supposed to be used as a wrapper for generally anything, and hopefully they make it as efficient as possible. But yeah. I really wish I knew how far it had gotten, but setting a breakpoint would interrupt the timing, which is bad. Although if I did it really quickly, it would only add like a couple of seconds to the potential output. It would be except I didn't attach a debugger to it, so that's a problem. I don't want to do anything that would seriously upset the timing. Curious, isn't it? All right. I'm going to attempt to attach a debugger. Attach to process. This is going to interrupt things and upset the timing a little bit, but I should be able to figure out what's going on, and then I can detach and let it go on with its life. That would be... Let me see if I can find it. The heck is it called? Oh, no, finally gave an answer. Look at that. It took 475 seconds. 4 times longer, about. Because I wrapped it up in this generator. Yeah. Intriguing, right? Especially intriguing because this kind of sort of deferred generator where we've got some sort of state that's operating that is being updated. It's being mutated under the hood in order to be able to produce the equivalent. Did it actually get the right values here? Let's see, 1593, which I believe is the correct amount. It looks like it got the correct values at the tail end of this. That's fine. I unfortunately don't have a window to compare it against right now, but I'm willing to bet that that's correct. And I'm willing to bet that the reason that the looped version is so efficient and this one isn't is because the compiler can't intelligibly see past the fact that I'm maintaining state for these loops manually. Can't place them in registers appropriately. Can't get past an optional value type, and it's probably the case that I'm not going to be able to make that faster just by getting rid of that clever optional value type. What I could do, though, just for giggles, you understand, let's actually have bool finished, and initially it's false. And what I'm going to do is I'm actually going to separate this out. So the get next is only going to return the value type directly. So I'm going to separate this out in some way here. I'm going to say, okay, no, I don't actually need this state. What I can do is I can say bool has value const return c is less than or equal to n, because anytime that that's true, this generator is effectively valid. Given that, what I can do here is I don't have to do all this make optional stuff. I can simply do return this, provided, so we can do bool has value, I'll have value type get value const return value type ABC. I can push more of this a little bit outward and try to get out from under this optional type, which I don't, it's so pretty, but whatever. Like from a, I like it as a mechanism. I think it's neat. But it's clearly not doing the thing we wanted to do. So optional value type, we're going to say next, void next. So that's only going to update the counters, at which point we have to make a separate call in order to be able to determine whether it has a value, and then if so, get a value. That way we're not constructing a wrapper object and then unwrapping it if it's valid. I don't know. This does seem more C-like, C++-like, kind of. I just like being a little bit more modern than this, to be frank. But, needs must. So what we're going to do is we're going to we're going to set up the conditional generator, and in this case we're actually going to start it at the correct values, because we're not going to call next. We're not going to call next until we have already processed a value. So we are basically going to do something like we're actually going to use a for loop because we can. We're going to say basically for auto g equals this. G dot has value. G dot next. How do you like them apples? Except I don't think it likes the G for some reason. The object has type qualifiers that are not compatible within the member function next. Why is that? Because it can't be const auto, and because next mutates G. So that having been done, if it even gets in the loop, G automatically has a value. So then we can just basically go equals G dot get value. Now this is a temporary, what I'm getting back from this, but I'm allowed to get references. I think this is illegal because I am allowed to get references to temporaries, and as long as I'm referring to it, the temporary lasts as long as the references do, I believe. And I'm just going to verify that because I don't want to write illegal code. That would be kind of terrible. So this is going to be C++ reference to temporary. Const reference, very specifically. It has to be const because you can't mutate a const references to temporary objects. C++ provides an interesting feature. This isn't a blog, so this isn't official, but provides an interesting feature where the lifetime of a temporary object can be extended to the lifetime of the reference which points to it. So, given that I'm doing a const reference specifically and structurally unbinding, and this is a temporary, because it's being returned by copy out of pi triples, and in fact, even in here, it's a temporary because it's a constructed value type. It's not a local; it's actually a new value, so that's fine, and that's actually going to end up getting returned by. That's going to get returned by value, which is probably going to get optimized away because it's going to be inlined. Can I return a reference to a temporary? I don't believe I can because it's on the stack, and that would be bad. But the value that gets returned is actually on the stack in the right spot. Like this is on the in principle on the stack in the stack frame of this function, but the return value is effectively on the stack of the calling values on the calling functions. So this should all be legal. I'm just going to make sure. Right. Yeah, I'm just taking a look. So yeah, I can't. I mean, this kind of makes sense, right? I couldn't return by reference here in any way because this would be constructed in the wrong spot in order to return a reference to it. That would be terrible. But I can return it by value, which should be optimized away, and then that's effectively a temporary at the calling site. Which you shouldn't normally be able to take a reference to because references to temporaries are bad, but C++ does allow extension of the lifetime of a temporary, provided it's a const reference. So, yeah. Temporary created to hold a reference initializer persists until the end of its references scope. It only applies to local const references. Anyway, that was more for my own education, because I could probably do copy outs and it would optimize that away too. So we are going to try this variation, and the first thing that we're going to do is just run it on a shorter size just to make sure it produces like a result in any sane amount of time. So we're just going to run that. It produces a value 158. It looks like it's correct, and it just finishes and everybody's happy. So let's try this. Let's make sure, double check that I am only doing the one that's relevant. That's right. Okay. Start without debugging. Go, do your thing. Oh, and once again, that window isn't available for viewing. Okay, so let me. I do have to keep an eye, very close eye, because I can't seem to get OBS to behave itself on Windows all the time. I like to actually write a custom. Oh, it did. I stand corrected. I'd like to write a little bit of custom logic and on how it chooses its windows to display. It's pretty smart, but it's not infinitely smart. So I don't know how long that's going to take. Let's go quickly poke back over to the time it stuff. This, unfortunately, is not going to evaluate all the values along the way. So what I want to be able to do, I want to be able to visit I think I'm not going to write this myself if Haskell provides a built-in, so what I need is basically a version of the SEQ sequence operator. Deep evaluation of data structures, but I don't want to go super deep. I only want to go as far down as one level of the tree. So force is evaluated to deep segments useful in some circumstances. Yeah, I don't want to, in this case, a fully deep force. But for our purposes, actually, what it might behoove us to do, because we're only really dealing with lists of integers anyway, is to use a deep sec. So time at deep, we're going to call it time at deep, and it's actually going to operate on anything. We're going to redo this here. It's going to operate on anything, but instead of evaluate, we're actually going to use. Let's see, we need deep SEQ, I believe. So basically, generally in Haskell, you don't worry about, you only worry about forcing an evaluation when you actually need the value. There are some cases where you want to force a value when you don't immediately need the value because you want to prevent those thunks from building up. For example, if you do a fold like I did with the append operator, you may not want during each layer of a fold. You may not want each layer of a fold to fully evaluate, to lazily keep building up thunks. Like, for example, if you try to fold a bunch of numbers like I did with plus, and you don't do it, if you don't do it strictly, you can end up with 1 plus 1 plus 1 plus 1 is a big honking chain of thunks that's not evaluated until after you need the actual sum at the tail end. That's why I use the fold L tick version of fold L, because the tick version is strict in its evaluation. There are things like that when you're writing functions where you might need to evaluate an intermediate quantity just to keep thunks from building up. In this case, what I want to do is evaluate an intermediate quantity in order to get the timing of the full evaluation of that thing, rather than just return a thunk like really, really fast, which takes no time at all. So we have to do effectively what amounts to a forced evaluation just for the sake of the timing, and we don't really care about the value. But we also want to go deeper than just the list, because evaluating a list only gets as far as the list itself. It doesn't go into its elements, and it doesn't go into its tail even. So I think we want to do this. And I think in order to get that, we need to import control dot deepsec. And control.deepsec should give us the deepsec function. Yes. So let's go check out the console. The console says that took 300 seconds on the C++ side of things. That's faster. That's quite a bit faster. So trying to get stuff out of the way of the optimizer that's getting in the way is obviously a key thing. That generator operation is not a bad one, and in fact, on certain kinds of generators, it may be when it's not just a for loop, where it's a little bit more complicated than that. The only reason it might not be actually that bad, and the reason why this one is slow is just because the simple nested for loops is just so easy for the compiler to see. And this is an interesting point, right? Because with this, the compiler can see all sorts of ways to optimize it. With this, it can't, because there's at least a couple of functions in the way, and now we don't even have that complicated structure in the way to hide ways that it can optimize, but it still can't optimize it all the way down to the rails. And I find it fascinating, once again, that back in this one, this function here, this isn't my fastest, but it's my these two are my second fastest. These both behave about the same. But this one does the filtering inline. This one clearly doesn't do the filtering inline, at least by way of the way the source code is written. Both of these perform the same way, which means in this case, Haskell is able to manage somehow to get this filter sort of buried deeper within this filtering. I could have to guess, because these two behave roughly equivalently. Now they're not equivalent to my fastest one, which and I'm kind of curious as to why that's the case. But the difference is about 10% ish between this one and my fastest. And my fastest was number 2, as I showed you guys before. But number 3, that bastard child version, this isn't the slow bit. It's the fact that this happens afterward. You tell me why. I don't know why. Like this one can't optimize, I think, because it can't push this filter deeper into this thing because it doesn't know how. It doesn't have the code rewrite rules. The fact that it does have the code rewrite rules to figure this out and get that optimization boggles my mind. Like, seriously boggles my mind that it can see through that. and I think it can see through that, because it can basically know how these functions, like filter and list production, can push values that are being evaluated only once out of the loops, and push values that might be useful to get deeper into the loops, so that so it doesn't have to reevaluate stuff. So yeah, that still boggles my mind. Nevertheless, what can we do to this conditional generator, or this style of programming, to make this feel more sort of value production-y, I guess? Can we maybe change, like, instead of being imperative, can we turn this into something that doesn't require, it's a bit more, I don't know, mathy? So let's copy this. Actually, let's copy both of these, because we're going to do this as a separate test. And this, I think, will be the very last thing I do this evening, because I want to go and do other stuff. So we're going to do conditional generator 2. It's going to be created the same way. I guess I don't technically need that tuple entry, but I didn't need it in the other one either. I'm just going to leave it there for the moment. I'm going to leave all these mechanisms in here as they are. Conditional generator 2, generator 2, generator 2. And then I'm going to pilist by generator, and let's just find out where I'm using that. I have to clone this code because I'm lazy and didn't want to factor this out. Yep, and yup, and yup, and yup. And yup, and yup. Pilot by generator 2 timing. And then here I'm going to do comment this out, because we're going to do this one and hit build. And it builds fine, because effectively this is just the same code. I haven't done anything clever here. So what I'm going to do to be clever is I'll leave the interface the same, but maybe I can do A is equal to A is greater than B 1, otherwise A plus 1. Except that if that happens, I have to reset B. So that's the problem. If the conditional happens, I want to set both A and B. So I wonder if I can try to do this. Structured binding. It may not like this without me making new variables. No, because it considers this an attribute. It doesn't consider this a structured binding. Because I would have to do... I think I can do this. Actually, I can just do a couple. I really wish I had Haskell syntax for tuples, or even C#. It'd be a lot prettier, but you know, needs must. We are going to make a tuple out of 1 and B. Sorry, if it's greater, it's going to be 1 and B plus 1. Oh, except that, look at that. If B gets altered, then I also want to alter C. So I'm going to have to set all 3 of these at once. Okay, let's this is going to look stupid. This is going to look really stupid, but let's give it a go. So actually, the first thing I want to test is whether or not I can do this. std make tuple 0, 0, 0. It's just making this more complicated, but it's also making it more mathy. So let's figure out if this is a thing. Expected a declaration. See, that's the problem, is that structured binding has to be done with new variables. So I am doing all 3 at once, though. So auto A2, B2, and C2. This is stupid. Right. If... Can I even semi-sanely do this? The only way C gets altered is also when A is less than B gets altered. So we're going to do this way. We're going to do the easy case first, which is if A is less than or equal to B, then the value is going to be just basically A plus 1, B, and C. Except we have to auto increment. So if A is less than B, then we can increment it. And we are effectively golden. That's where we're done. Because A is allowed to be equal to B, so that's the last value where that's actually legal. Then we're going to have, and actually I'm going to separate it out this way. It's going to be funny if it actually makes no difference to the operational behavior of this. Let's see if it can optimize through this value expression. Otherwise, if we know that A is at least greater than or equal to B, so, but when that happens, like A plus 1 would end up being greater than or equal to B. So that, and then we're going to have a situation where we want to increase B. So there's two options here. If B is less than C, then we are in a situation where B can be safely incremented, actually, so it has to be less than C minus 1. So we're going to say that this means that std make tuple is going to be 1, because we know we're going to have to reset that. We are then going to have to go to B plus 1, but we're going to leave C alone. Finally, the result is going to be std make tuple. This is, we're going to be resetting C, so this is technically still going to be 1 because we knew that was going to be the case. This is also going to be 1, and this is going to be C plus 1. So that, in principle, should generate the same values, but doing it with a value mechanism rather than doing it by way of... this is a purely functional approach to building this. Problem is there's a lot of repeated variables here, and it's not clear to me how well it's going to optimize this. But it also doesn't have to optimize through statements. This is all value. So let's find out. Except that we also then have to do A equals A2, and B equals B2, and C equals C2. So that's the downside to this, is because I had to make those additional variables. That's what I end up with. Although these are all temporaries, right? And not only that, they're const temporaries, and I could do that. And what that means is that these are going to compute values, stuff them in references, and because they're const, maybe they can just be directly assigned. I don't know if this is going to be any faster. It'll be an experiment. Yeah, all right. This is strange, but who knows, right? Once again, though, we have to, let's just run this on a much smaller data set. Say 1,000. 1,000 should do. $158. It is correct. That's conditional generator 2. So how do you like them apples? A purely value-driven version of that. That's kind of wild. So let's just make sure that let's actually just make sure that we're getting into this version of it. Yeah, so that's where we're getting into. That's fine. We're getting the value out, we're building a triangle, we're doing all of that. It is using the new version of the class, and so once again, let's just put a debug statement in here, make sure that we're getting in here. And it's not, and why is that? because it's optimized this away completely. All right, let's go back because it may be optimizing this away completely, and we're just going to turn on the debug mode temporarily, and you might not be able to see this, but it is getting into that code. So the reason it wasn't stopping there is just because the debugger just didn't have a place to do its thing. So going back to release mode and one more run just to make sure it's not stupid. That's fine. All right, so we're going to do a run on the big number again and see if doing that by values has even further enabled it to peer into what's going on there. Sometimes that might be the case, but it also has to do some additional weird work because of repeated variables in there. Not so much repeated expressions, but let's find out. And tuple's kind of complex. I could probably do that with a struct instead, maybe. Start with debugging. Not really expecting this to be super fast. No, except you can't see that again. Maybe. OBS. Nope. OBS says you can see it. Yes, it's popped up. Everything's delayed. It's about a 5 or 6 second delay between the time that I'm talking and the time stuff appears on stream. I thought it would actually have been faster. Like the lag time would have been lower on Twitch. Especially because I have the low stream latency flag flipped on. But maybe I have to fiddle with it and tweak a bit. Oh, it looks like I've mislabeled this as Playground 0001. It's actually 002. I will have to fix that label. Huzzah! All right. So that's running. Is there anything else that I could do with this generator? This is a very Haskell-y way to do it. It's not so much a C++-y way to do it, except that a lot of the standard algorithms have gotten quite functional. And again, ranges in C++ will have a very lazy evaluation style, which kind of encourages a bit of a functional processing paradigm a little bit. So actually, let's take a look at this code and what it will actually do. It'll try to do a binding of references to a temporary variable, which means that wherever this gets sort of built by the compiler, it'll just temporarily use them. It doesn't have to copy them into individual variables. So it should be able to optimize away that reference. It shouldn't be a pointer access or anything. It's only ever going to make one of these, but then it has to reassign them. So the speed of this is largely going to depend on whether or not it can optimize away this assignment. Doing some clever register management in here, and whether or not it can find the situations where it doesn't have to update a variable. Because there's some situations in here where we simply leave variables alone, like here and here, right? So it's just going to copy back the same values. The question is that going to impede the performance of this thing? When I was doing the explicit if conditional, which is up here, I only ever updated the minimum number of variables necessary, but it also meant there was a lot of potential jumping around this stuff. I'd have to look at the assembler to see exactly how it solved this, because this is going to be pretty efficient if it can use instructions that don't require the jumps in order to do these operations, or can get clever about that. There's no fewer jumps necessarily in this one. The only difference is that I'm not using an imperative style, so it might be able to use that to its advantage, perhaps. Highly interested to see what the result of this is. I expect it to actually be slower, but... I am putting a tuple in the way of this. Optional is a little more complicated. Tuples is, I think, a little bit simpler, but it's still a complicated structure. Maybe I could use I don't know if I can I structurally bind? That's a good question. C++ structural binding to struct. binding an array, binding a tuple-like type. It doesn't say necessarily tuple, but it does say tuple-like type. Interesting. You have to, in order to make your own structure deconstructible in this sense. Oh, look at that. We got a result. 191, no, it's 200 seconds. That's getting closer. I can't remember what the first one was now. I think it was 300, wasn't it? That's actually better. Okay, now I got to run both side by side because I don't actually remember. That's curious. That is highly curious. Highly curious. Interesting discoveries, right? What can compilers get away with? And again, I'm not really interested in the absolute number, but the relative performance of different styles is kind of interesting. If I really wanted to make this super fast, I'd really go to town on it. That's not really the point. All right, we're going to do conditional generator timing and biconditional generator timing. And this is going to take a bit because it's going to have to do both. I really should just go and do other stuff this evening, but this has just been too much fun. All right, here we go. Okay, stream can apparently see it. Fascinating. So yeah, in order to do structured bindings on your own types, you have to supply some compile level information in order to be able to pull out tuple elements. So you can invent tuple-like types. Isn't that fascinating? That's kind of neat, actually, where at the type level, you can effectively supply enough information to allow types to be processed by specific mechanisms. Like the ability to do structured binding at the compiler level, because that's a specialized syntax, as long as you identify how it behaves like a tuple, and you do that at the type level, not at the runtime level, you can then extract the relevant. You can do structured bindings like that on your own types. At least that's what that kind of implies. Without incurring any runtime costs, which is sort of the point. All right, that's going to take a few minutes. I really do have to put this down, though. So, having done this, so let's before that finishes, because it is going to take a few minutes, let's take one last look at this. So, basically speaking, the very fastest version of this was clearly scrolling. It's clearly this guy for the C++ side. This guy finished in about 120 seconds. I'm tempted to think back and remember to go through all of this, and partially optimized, I think, because it can see all the for loops. There's nothing in the way, and the test is right buried in the middle. The fastest Haskell version that we had more or less did a similar thing. All of the loop constructs were explicit at the same time. They were all done recursively instead of iteratively, but that didn't impact it poorly. And it had the tests all the way in the middle, buried. The other two Haskell versions that were interesting were effectively about 10% slower, but syntactically much, much prettier, so probably worth it for anything except the tightest possible code, which is kind of what you want. And that used a list comprehension to just generate the relevant triangles. And one of them even deferred the filtering until afterward, which was kind of interesting. And that suffered no impact. Even though another function where we had the explicit loops but deferred the filtering was impacted really, really badly. So highly fascinating result there. But the purely sort of the most Haskell-y style that at least involves list comprehensions and nothing else super exotic, in the ballpark of an optimal implementation, and really easy to write. Over on the C++ side, simplest possible version was the for loops that you see here. Way wordier than the Haskell version, slightly arguably more performant than the Haskell version, maybe. We're still having some timing issues to figure out to make these comparable. But not super significantly so. And although it's pretty easy to read, it's certainly not lazy in any sense. And the nesting of the for loops like that kind of looks a little gross. I mean, it's clean in the sense that it's really easy to see that there are 3 for loops. But who wants to do nesting like that if it starts to get deeper, or if the looping constructs are more complicated? That being said, though, in an attempt to do types of conditional generators to lazily evaluate the lists, lazily evaluate the indices, in order to generate them one by one, even though we built the whole list all at once. It's not quite that lazy, obviously, as Haskell is. The performance suffered terribly, getting up to like 500 seconds or whatever it was. When we updated the conditional generator to attempt to in an attempt to turn it into a more value-oriented thing, which is sort of a style that you would actually expect from a Haskell program, we got some of that performance back, actually. And I think it's partially because of 2 things. One, we managed to get around having complicated structures in the way that was probably making optimizations more opaque to the compiler, something Haskell didn't suffer from, incidentally, at least not in that form. Which isn't really a mark against C++. It's just hard to go through opaque types. And Haskell's used to processing lists. This got a benefit, I think, because not only were there not complicated types, but we had a purely value-oriented update to the state, and we didn't have what is essentially imperative stuff getting in the way. Now, I would argue that the compiler maybe should be able to see that it was a purely value-oriented thing, but we made it very explicit here. I'm hoping make tuple and the accessing of the values done by the const referencing were also highly optimized away. And you could argue, well, okay, you're just introducing a complicated type in there. Yeah, maybe. Still seems to have performed better. I'd like to get an actual result out of this thing. So we got 300 seconds out of the first generator, which used an if-then style, like an if-else style, right? It's actually trying to outguess the compiler by implementing only the exact steps necessary in order to update the state. Everything else is identical. The only difference is how I update the state, and in this case, not only am I updating the state through this value mechanism instead of the strict if-else, like the imperative style. This value style actually, in principle, has assignments to values that have not changed. That's kind of fascinating. I'm kind of curious, actually, if there is a way to make this even faster by telling make tuple that it can store references to variables, possibly const, so that it can hold references to temporaries, so that the compiler can identify when I pass in B that it's actually referring to the original B, so that they can then negate this under some conditions. I don't know, because the minute it has to make decisions on which ones to copy and which ones not, conditionally based on what happens here, maybe that's possibly what's slowing it down. And the fact that I'm doing it this way means that it can do everything inline. The inlining may be the thing, right? Because it can probably do batch assignments of variables like that really, really fast. any decision point to change a piece of memory or a register might slow it down. This has to make 2 tests, but then on making one of the tests, it just does possibly 2 really quick batch assignments. Fascinating, right? And if it has to do 2 tests, it still has to do only, effectively in every case, it only has to do a building of the tuple, which may be all done in registers without decisions, and then immediately afterward it moves them all back again into possibly other registers. And then maybe the optimizer can take a look at that and say, okay, I moved B from register R3 to R5, and then moved it back from R5 to R3 in this case, and so I don't know. Curious, right? 192. It is in fact 33% faster to do the value version of this, of the generator. That's still not half as fast as it was at 120, but it's basically what is that, 88%, 80, 90% faster or slower. Calculator. Can't do that in my head anymore. I'm getting too tired and ossified and old. So what I want to say is 200 divided by, that's the times key, buddy, 120. 1.6 times slower. Like it's that much slower to do this than the nested for loops. That's terrible. I suppose it's not bad given that this is a little bit opaque, and in a non-performant bit of code, I'd be okay with that. That's fine. But this is a performant bit of code, so the question might become, so this is unable to optimize away the fact that I'm doing this state like this. Yeah. This style is not capable of being optimized in quite the same way. Not for this simple case. Don't know why. I haven't dug that deeply yet. Fascinating, right, though? I just wanted to come up with a bunch of test cases. Right. I'm going to call it here for this. So where I'm going to go from here. That effectively, as far as I'm concerned, addresses a lot of interesting stuff about how to generate the relevant solution to this. The algorithm is not the most optimal. I don't need that inner third loop. It's a silly thing to have in there. Obviously, I could get this down to an n-squared algorithm almost trivially. Not really the point. This is more about a style thing. And what the compiler could do and what the compiler could optimize. And I'm not sure going down to the 2-loop version at this point is really going to change that. But what I am interested possibly in is figuring out how you could use code reuse in a bunch of different ways to implement different versions of this, like piprint wide, piprint long. How can you do these things efficiently in terms of memory? I want to explore, for example, what it takes to maybe lazily write out really big versions of this to a file, and what that means in terms of memory usage and so on and so forth. How much, what kinds of effects does laziness have on it, performance-wise, memory usage-wise? I think that would be an interesting exercise. But the actual act of generating these into a list, I think we're done here, for the moment anyway, until I decide to update the algorithm in question. So what I'm going to do is for the next video, I'm either going to go into looking at how to write the other versions of this using one of the more performant versions of what we have, and probably I'll stick with the loops version, explicit loops version in C++, because it's really easy to see and understand. At least initially, I'm going to stick with that. And probably I'll do the list comprehensions thing on the Haskell side. Or alternatively, well, we'll have to see, because a lot of these things are going to require either injecting operations that I need done on the list on the production into the functions themselves, like those filters, in order to get good performance. Or I'm going to want to have to do some sort of lazy evaluation, because if I want to output to a file a million such elements, I may not want to actually store a million such elements in memory, because that would be kind of silly. So how can I do this incrementally? How can I do this lazily? Might be interesting to explore those operations from the point of view of these two languages. However, we'll have to leave that for another time. I may change my mind on which puzzle that I want in order to do that. But if I change the puzzle styles, then I will try to pre-solve that puzzle in the two languages, so that we don't have to go through all of this again. When it's not the point of the focus of the project. So this is where I'm going to call it. All right. So, wow, that was an interesting hop all over the darn place. Lots of interesting behaviors on the part of the compilers. Lots of places where we can do improvements. I really kind of want to actually get into a puzzle where I can more easily use the standard template libraries, algorithm functions to help do some of this, because that bears more resemblance to some of the link stuff and the range stuff, and I think that's good solid code abstractions beyond the typical object-oriented stuff. Because this one boiled down to something a little bit simpler than I'd thought. One line in Haskell with some support functions for filtering, and what essentially amounts to one line or a couple of lines wrapped by some simple for loops in C++. Looking forward to doing more code live with all of you. Don't know when that's going to be, because I have a day job and my vacation's over. But I have enjoyed this too much to not do it anymore, and so I'm going to mix this in with my game streams. Thanks very much. This is Code Weaver on Code Weaver Writes Code, and I will see you in the next stream.